All right, we'll get started here. Welcome everyone. It's great to see everyone, some familiar faces and some new faces. My name is Sean Collier. I'm the current president of the North American Weather Modification Council. Let's see, I want to thank Kayla and the Idaho Department of Water Resources for the lend of this room. It's a beautiful facility, and Kayla for doing a labor of setting this up and getting everyone to come together. I think we're going to have a great day today. We have some goals today. We want to talk about weather modification or cloud seeding. And generally, those terms, you'll hear both of those terms used. And generally speaking, you can use those terms interchangeably. But sometimes there's a few little nuances there. So you'll hear us talking about that. We're going to go through why do a cloud seeding project? What is it? What do we know? What don't we know? And just go through the process from if you're thinking of doing a cloud seeding program. We'll talk about going through and picking out a site to do that, a target area, and checking to see to make sure that's working, the effectiveness of it. So we have some really good, probably the foremost experts in the country and among the world here in this room today. So we're really fortunate to have that. I'll just talk really quick about the North American Weather Modification Council. We're co-sponsoring this with the Idaho Department of Water Resources. Our mission, and I didn't get in time, this didn't copy and paste over correctly. Our mission is to advance and promote the proper use of weather modification technologies through education, research, and education and research. So we have many members. We formed in 2011. I'm the current president. I represent the Southern Nevada Water Authority as a member. Jake Sarago is here in the room here back there. He's our vice president. Mike Schneider is our secretary, making sure everything's being recorded. And Julie Gonzar is our past president with the Wyoming Water Development Office. You can make it today. So our members are comprised of agencies or entities that have, they have regulatory, operational, or programmatic controls over weather modification projects in their states or provinces. We have some, we had some folks from, I think, Canada at one point as a member. So any agency associated with weather modification. So here you see as a list of the members from all over, mainly the Western United States. So just really, really fast, I know there's some other folks doing one-on-one talks, and you might see this picture a few times in other presentations. The origins of cloud seeding. So this concept was first discovered by a person named Vincent Schaefer and another person. He's the guy looking at the. So what you're seeing here on the left is it's basically a chest freezer, to simplify the terms, where they had a icy fog in there, and they put some materials in there to see if they could get the fog to turn into the precipitation. So you have Vincent Schaefer looking in the chest. You have Bernard Vonnegut there. He's the brother, actually, of Kurt Vonnegut. That's Irving Langmuir, I believe. So it was after World War II, and they, from the story I read, is Schaefer was looking for, he was investigating icing on aircraft, which, was, being up here, you're very familiar with that. You're always being de-iced and everything. But they were researching that and noticing the behavior of the particles in the clouds and how they were icing, and then it sort of came up with an idea. It's like, well, can we make this come out of ice out of the sky? So they later used a modified B-17 bomber, and they dropped some dry ice out of the plane. And that picture on the right is you can see the effect in the cloud bed there. Just coincidentally, this was in, I think, Schenectady, New York. I grew up like literally across the river from the laboratory for General Electric, where they developed that, and this test was done, I believe, over the Berkshire Mountains in Massachusetts. So I consider myself the relative newcomer to this science, and so I think people will go into a little more depth on it than that. But I've found like talking about the purposes of cloud seeding. You're going to hear about warm season cloud seeding that's used to increase precipitation. It can be used for hail suppression. It can also be used for fog abatement. We saw a really interesting project up in up in Medford, Oregon, where they were using using a balloon and some dry ice to sort of increase the visibility for aircraft to land. So there's all kinds of interesting purposes for this. Cold seeding is what mainly got me drawn into this world. That's to increase precipitation and snow. So you see this map here. I believe it's pretty up to date with a lot of the projects that are going on in North America. You know, the green shapes are if they're doing it for increasing liquid precipitation or for hail abatement, and the blue is for the cold season seeding for holding snowpack. And I'll talk about more specifically about some of the seeding that occurs in the Colorado River Basin later on today. But that's everything I have. I would just also add that you know, as water professionals, we always look at the hydrologic cycle. You learn about that in school, and there's you know, you have in a given water basin, you have inflows of water coming in, and you have outflows of water. A lot of when the question comes up of, well, if we have too many people or too many crops, how do we get more water out of this? The first answer is always like, okay, well, let's look at the out part. Let's do more conservation, which is great. You know, let's do maybe land fallowing to bring that back in balance. But cloud seeding is one of the only ways, or weather modification is one of the only ways that, without building a pipeline from somewhere else or diverting water from somewhere else, to actually bring a little more water from the input aspect of it. So that's what you're going to hear about today. And is it going to solve all the water problems in a basin? No. It's a really good tool to have in the toolbox of water management, I believe. So you hear more about that today. And then I'm going to pass it off to Kayla for the first session.
All right, good morning, everyone. My name is Kayla Golden. I'm with the Idaho Department of Water Resources, and I represent the Idaho Water Resource Board as their cloud seeding program manager. So as your host today here in Boise, I will be your tour guide this morning. I'm going to walk you through the agenda and what we have for you today. I'm going to start by saying, you know, this workshop that we have put together, I've asked each of our speakers to take a step back and think about, you know, if I were a water resource manager, if I were a stakeholder or a policy leader who has never been exposed to cloud seeding, and I've been asked to either approve funding, to start a program, or to contribute in some way, what are the basic things that I would want to know? And so today we put together about 3 different panels for you. This first panel is going to go over the basics of cloud seeding 101, the current state of the science and what type of operations. We'll do a break at 10:15 and wrap up the cloud seeding 101 portion, and then cover some environmental topics and do our question and answers. So the next panel that we will have is on developing a program. And this is not meant to be sort of a step-by-step for how you develop a program, but it's rather a comprehensive collection of all of our expertise, all of us who have participated in cloud seeding over the years. And this is basically all the information that we put together that we feel would be useful for somebody who has never been exposed to cloud seeding before and may be considering developing a program. So we'll cover some of the basics of breaking ground, feasibility and design. After lunch, we will break at 12. After lunch, we will continue with developing a program and cover some of the basics of program implementation, monitoring, and analysis. And this does include how do we evaluate cloud seeding, how much, what is the increase in precipitation, or how do we know what the impact is. In the afternoon, the last portion or last panel that we'll have for you today is the collection of our existing programs. So you'll hear from program managers across different states on how they operate their programs, how they started, how they're funded, and some of the challenges that they've faced as well. So our last panel that we'll have, the final Q&A, will be for the entire workshop, a chance for folks to ask questions of our speakers today.
Okay, so everyone complains about the weather, but today you're going to hear about people that actually do something about it. You're going to hear from top scientists, longtime operators, enthusiastic project sponsors like me, with collectively hundreds of years of experience in this field. I want to add one thing to what Sean said. The council, the North American Weather Modification Council, we've actually been meeting since the 1970s in one form or another, but in our latest incarnation is when that's what Sean was talking about. I want to set some expectations. If you think that I'm going to put in some money up here and it's going to end up with acre-feet of water with my name on it over here, that's just not going to happen. What we're going to do, we're going to talk later about the cooperative agreements, models of cooperative agreements, just like on the Colorado River, for example, where everyone agrees it's system water. And the science also isn't there. We can't quantify what's going on and identify. We identified all the links in the chain that need to occur when someone says, I'd like to do some seeding in this area, and then here we have the output over here, but there's still work that needs to occur on a lot of those links. We've been able to prove some of them, but others, the science isn't there yet. But today you're going to hear about the state of the science, and you'll know what we know and what we don't know. The bios of the speakers are in your packets, and so I'll just introduce the folks as they go. One final thing, one final story. So I started a program at the Winter Park Ski Resort in Colorado, and they were very happy with it. And then I thought, well, let me start one here at Telluride. And so I asked Winter Park if they would come with me. Will you come with me and tell Telluride how much how much you like the snow that we've been generating? And they said, are you nuts? This is our secret weapon. We believe this is what gives us the edge. I'm not going to go help you help our competition. And so that's a testimonial on how folks really like what we're doing.
So I'll be talking today. I'll probably be giving the only talk that doesn't have anything directly to do with cloud seeding. I am tasked with discussing some of the basics of cloud physics, what we know about cloud physics, which will set the stage for the later talks that you'll be seeing this morning in regards to how do we actually modify clouds, right? Because we start with a base state of how clouds evolve naturally, and the idea behind cloud seeding then is how can we modify them in such a way to alter their evolution and produce precipitation that otherwise would not be produced. So I'm going to start very basic. When we look at a cloud, what is a cloud? What is it made up of? Okay, what do we see actually when we look at a cloud? Do we see water vapor, or do we see particles, or what is it? And are all clouds the same, right? Are they made up of the same thing? And short answer is no, they're not. Some are made up of ice, some are made up of liquid water droplets, some are made up of combinations. The cloud on the right is almost entirely ice. The cloud on the left is almost entirely ice. The one on the right is almost entirely liquid. And what we see is we're actually seeing those small particles in the cloud, okay? We're not seeing the water vapor in the air. Water vapor is invisible, okay? How do clouds form, and why do clouds form, okay? Clouds rely on natural processes that are occurring in the atmosphere and kinematics in the atmosphere that lift the air, cause the air to cool, and lead to the formation of a cloud. So rising air is important to the formation of a cloud because when air rises, it expands. Okay, you take a balloon and you put it in your car and you drive up to the top of a mountain. That balloon is going to get larger because the air pressure is lower around it. As that air expands, it cools. It cools not because the air around it is cooler. It cools as a basic principle of physics that when you expand a gas, that gas cools. Okay? As that gas cools and the temperature drops, okay, the relative humidity in that balloon is going to go up. And as the relative humidity increases and gets closer to 100%, when it reaches 100%, okay, the water vapor that is in that balloon will begin to condense. And then we have a cloud, okay? It will be composed of liquid water droplets, condensed water droplets that form from the water vapor condensing, and we have a cloud. Okay, so most of us probably know some aspect of this story already, okay? What's the big deal, okay? Clouds are made of tiny droplets or ice particles The real question is not how the cloud forms, but how do we get from a cloud that is composed of very, very tiny water droplets or ice crystals to particles large enough to fall out of that cloud and form precipitation. So this schematic shows the small circle in the lower left as a cloud droplet. Okay, a cloud droplet is typically 10 microns or so in diameter. We cannot see a cloud droplet with our naked eye. Okay, we look up in the sky and we see clouds, but we can't see an individual cloud droplet. We can see a whole bunch of cloud droplets together that are reflecting the light. Okay. If you take a cubic centimeter of air, so we're talking about a packet of air that is roughly a half an inch by half an inch by half an inch. There are 1,000 cloud droplets in that cubic centimeter of air. Okay, maybe 100, but there's a ton of them. There's a lot of them. Okay, to go from a cloud droplet, which will follow the air motion and won't actually fall out of the sky, to a drizzle drop, which is maybe 100 microns. So it's 2 orders of magnitude, or it's an order of magnitude larger. It takes 1,000 cloud droplets to make up 1 drizzle drop. Okay, and the concentration of drizzle drops in that same cubic centimeter of air goes from 1,000 cloud droplets to about 1 drizzle drop per cubic centimeter of air. So there's a lot fewer drizzle drops. And that makes sense, right? Because you need a whole bunch of cloud droplets to form to make that drizzle drop. Okay? But even a drizzle drop, it doesn't fall very fast, right? If we're talking about producing precipitation or thinking about a useful amount of precipitation, okay, a drizzling cloud is probably not going to get us there. We need a cloud that actually produces rain, which is the large circle in the bottom right. And now a typical raindrop is 1 millimeter in diameter. Okay, and it takes 1,000 drizzle drops to make 1 raindrop. Okay, or if we think about going from a cloud droplet to a raindrop, it takes 1 million cloud droplets to get to run 1 raindrop. Okay, and the concentration of raindrops is 1 per liter, which is 1,000 cubic centimeters. So you take your little cubic centimeter and you get 1,000 of those, and you might get 1 raindrop from that. Okay, so the challenge in natural clouds or in cloud seeding is how do we get from these small particles that make up clouds that form very easily to these large particles that actually fall out of the cloud. And to answer that question, we need to know something about the processes that actually allow us to go from a cloud drop to a raindrop. And that's what I study. Okay? So let's take a couple of steps back first. Let's consider 2 types of clouds. That last slide I was talking about all liquid clouds. Okay? These clouds generally exist anytime the temperature throughout the cloud is warmer than about -5 or -10 degrees Celsius, 14 to 23 degrees Fahrenheit. If the cloud is contained in a region that is entirely warmer than that, or the entire cloud is warmer than that, most of the time your cloud is going to be all liquid. That's actually easy. We're going to start with that problem first. The other type of cloud are clouds that are made up of both liquid and of ice. Okay? We call these mixed phase clouds, and these are much more difficult. But these are the clouds that we deal with most of the time, especially here in the Intermountain West. These clouds have some portion of the cloud that exists at temperatures colder than, say, -5 or -10 degrees Celsius. It may not be the entire cloud, but if the top of the cloud is at colder temperatures, at, say, -15 or -20, chances are it has some ice in it, okay? And it also is very likely that the entire cloud is not ice, but there's actually a mixture of liquid and ice. We're going to talk about why that is. These clouds are really hard, but they're really important to precipitation in the mid-latitudes. Okay? So what this looks like schematically here is on the left-hand side, we have a cloud that exists with a top that's only extending up to about 23 degrees Fahrenheit, okay? And that cloud is entirely liquid, okay? It's super cooled liquid because it's below 0 degrees Celsius or below 32 degrees Fahrenheit, okay? But it's liquid. And then we have this cloud on the right-hand side, right, that extends a little bit higher in the atmosphere to colder temperatures, and it is composed of both liquid and ice. But we can see, you know, at least in this little cartoon, that the liquid can occur even at very, very cold temperatures in the same regions where there's ice. And this is important. This will be important in terms of understanding processes. And then there's somewhere between these two where a cloud might have some ice in it or it might not. And we'll find out later in this morning's discussions that those types of clouds are often the types of clouds that are really targeted. Or at least they've been targeted in the scientific studies to understand what's going on in cloud seeding. So let's start with all liquid clouds, okay? We already set the stage of, hey, how do we get to these small cloud droplets to large, or to a raindrop, okay? And it's really, actually, it's quite simple in terms of understanding the physical mechanism. So we begin on the left-hand side of this schematic with a field of very small cloud droplets, okay? And these cloud droplets differ in size a little bit. Some may be 10 microns, some may be 20 microns. And if they have a little bit differential size, they'll fall or they'll move around a little bit differentially in speed. And if there's turbulence in the cloud, it can cause those cloud droplets to collide, okay? And when cloud droplets collide, some of them will coalesce. When they coalesce, they come together and they form a bigger drop. And that bigger drop will fall maybe even a little bit faster, and it will collide with other cloud droplets. And it's a cascading process, okay? So as the particles get larger, they fall even much faster relative to the particles around them, and you can grow to a raindrop size. Very simple concept. So if we look at, let's say, a cumulus cloud, we start at the cloud base with condensation that is occurring, and small cloud droplets form as those cloud droplets, as that region rises through the cloud, and you get different cloud droplets that begin to collide and coalesce. They grow larger, and eventually they fall out of the cloud, okay, as raindrops. And they fall fast enough that they can fall faster than the updraft is pushing them up, okay? Condensation followed by collision coalescence can be a very slow and inefficient process. It can also be a pretty quick and efficient process, but it needs a couple of things, okay? This process works best in warm clouds that have lots of water, okay? So we see this in the tropics. We see this in the southeast United States, in Texas, okay? Where there is a lot of water present, and these water droplets can grow very quickly. In colder clouds, okay, there's not as much moisture in the air, there's not as much liquid in the clouds, and collision coalescence is pretty slow and it's pretty ineffective. So if we have a cold cloud that's, say, -5 degrees Fahrenheit, and it doesn't contain ice, it contains only liquid, okay, the chances that we'll actually be able to grow cloud droplets to a raindrop size is pretty small, okay? There's not enough time, there's not enough liquid to do it. And in addition to the amount of liquid water, okay, how many droplets are present and their relative size is also very important. And this will come into play, I think, when there's some discussion later on about the actual process of cloud seeding. Okay, so the last part of the talk is, let's think about clouds that contain ice, okay? These are hard, okay? This is an order of magnitude more difficult in understanding the natural evolution of clouds because there's so many other processes that can occur. In liquid, it's simple. Condensation and then particles collide, they get bigger. In ice, there's competing processes between what's happening with the liquid and what's happening with the ice, okay? So everyone knows that ice melts at 0 degrees Celsius. If I take ice and I put it in a box that is 0 degrees Celsius or warmer, it's going to melt, okay? The same is not true about liquid. If I take liquid and I put it in a box that's 0 degrees Celsius or -1 degree Celsius, it's not necessarily going to freeze. And in fact, it likely will not freeze until I get it much colder, unless I add something to it, okay? So in the atmosphere, as has already been alluded to, okay, liquid water drops often exist at much lower temperatures than 0 degrees Celsius. And in fact, they'll exist at temperatures as cold as -40 degrees Celsius, which is also -40 degrees Fahrenheit, as it turns out, okay? Unless there is some particle that is added to that liquid drop, okay? And it could be dust, it could be smoke, particles, okay, that help that drop freeze. Turns out, though, that naturally in the atmosphere, these particles tend to be rather rare. So at relatively warm temperatures, below 0 degrees Celsius, and let's say warmer than about -15 degrees Celsius, it's a gray zone. Okay, clouds often contain both liquid and ice. And the liquid is much more abundant than the ice. There's a whole bunch of liquid particles, and there's maybe just a few ice particles. So why do we care about all of this? Whoops. Okay. Almost all of the clouds at mid and high latitudes, where we live, okay, are too cold to produce precipitation from liquid alone. We've established that. Some of these same clouds are generally mixed phase. They contain a lot of liquid and a little bit of ice. In these clouds, ice has an advantage compared to liquid in being able to grow. So if I take an ice particle and a liquid particle in the exact same conditions, that ice particle will have a distinct advantage to growing to larger sizes than the liquid particle. And this is known as the Bergeron process, or the Wegener-Bergeron fine descent process. Okay, it's not important. You can call it the Robin Hood process, because what's happening is this ice is stealing, if you will, the water vapor molecules from the liquid drops. Okay, it has to do with the vagaries of saturation pressure in ice related to water. But what this means is two particles in the same condition, liquid and ice, this ice particle is going to grow, this liquid particle is going to shrink. And water vapor molecules are essentially going to go from the liquid to the ice particle. And this ice particle gets larger and larger. Now imagine that you have a field of just a couple of ice particles and a whole bunch of liquid particles. These ice particles grow very quickly. And then they can begin to fall out of the cloud. And so the colder clouds are unable to produce precip through liquid alone. Ice particles are relatively rare in these same clouds, but they often exist at temperatures at least as cold as -15, okay? And if ice does form in these clouds below 0 degrees Celsius, okay, those few ice crystals will grow rapidly and very efficiently transform into falling precipitation. So we're zooming in on a cloud here, and let's start off and zoom in on a cloud that we have a small cloud droplet and a small ice crystal together. In reality, we have a whole bunch of ice crystals, or a whole bunch of cloud droplet and a small ice crystal, and the little red dots are water vapor molecules. And what happens, right, as we go through time is these water vapor molecules go to the large ice crystal, and that crystal gets bigger and bigger and bigger, okay? Eventually, it gets big enough that it begins to fall through the cloud. And when it falls through the cloud, it encounters other cloud droplets around it. And those cloud droplets attach to the ice crystal, okay? Getting that crystal larger and larger, and then eventually it falls out of the cloud as a snowflake precipitation, okay? In the wintertime, it falls to the ground as snow. In the summertime, it eventually falls into a layer that is greater than 0 degrees Celsius and melts and becomes a raindrop. So that's all I have for you. I will turn it over to our next
All right,
speaker.
let's thank Dr. French.
Good morning, everyone. I am so sorry I can't be there with you all in person. That is life, I suppose, and I am still happy that I can join you remotely to share with you some of the exciting things that are going on in the world of science with regard to cloud seeding. You know, I'll talk a little bit about how it works and some of these recent advances in the research, but I want to thank Professor French for laying the foundation of the cloud physics principles that are really the basis for how cloud seeding is meant to work. To get started, I just want to upfront run through 4 key messages that I'm going to be making in this presentation that I hope, if nothing else, you'll take away these 4 key messages. One is that recent studies have proven that cloud seeding works to enhance precipitation in winter orographic clouds. And there have been a lot of recent advances in modeling that are enabling us to do innovative research and improve our understanding of cloud and precipitation processes, including cloud seeding impacts. More research, though, is needed to advance our understanding of cloud seeding impacts in summertime clouds. And cloud seeding effectiveness will vary by storm and by location. So it's really important that we do feasibility studies, because just because we know that the concept can work doesn't mean it's going to work the same way and that's the same magnitude everywhere. All right, so getting started, I know Sean presented this map earlier. I just want to start out with that basic understanding of what is cloud seeding being used for, and it's typically a technology used to enhance precipitation. It is being conducted in many places of the western United States, especially those shaded in blue are focusing on cold season or wintertime cloud seeding, generally in the mountainous regions. We also have places in North America focused on summertime cloud seeding, as shown by the green shaded areas. And it's happening around the world as well. And I just have a few countries listed here, but it's happening in many places around the world also. So starting off with winter orographic cloud seeding in particular, how do we seed winter storms? Well, there's 2 general modes for this type of seeding. The first would be to insert ice nucleating particles. As Jeff just explained, ice particles are not as high of concentrations as they could be in order to make that ice process as efficient as possible. Usually for this purpose, silver iodide is a commonly used particle because this ice nucleating particle has been shown to nucleate ice at relatively warm sub-freezing temperatures compared to where natural ice nucleating particles are forming ice. The other mode would be to create a supercooling effect to nucleate ice. And so this would be to use a material, generally dry ice or liquid propane have been used for this purpose, to create a really intense cooling that then brings that temperature down so cold that it nucleates all potential ice nucleating particles that might be occurring in the region. This second method has not had a lot of research on it lately, and so I'm not going to be focusing a lot of this, my presentation on it, but I will point out that there are some renewed efforts to look into this mode of seeding winter clouds. Otherwise, I'm going to really start talking a little bit more in depth about the silver iodide mechanism for seeding winter clouds. And just a quick note for those in the room, is there a way to mute your microphone? Because I'm getting a lot of background noise coming in, including cars driving by. It's a pretty sensitive mic. All right, so this is diagram walking through the steps of the conceptual model for winter cloud seeding, especially with silver iodide. That first step is that we need a cloud to form. These clouds generally form over the mountains due to the airflow rising up and over the mountains, as Jeff mentioned earlier. We do not create clouds to cloud seed. So this is a very important first step that we need. The cloud also needs to contain supercooled liquid water. And so also, as Jeff walked you through, not all liquid will freeze immediately when it reaches that freezing point, and some will remain in that liquid form even though it's colder than freezing temperature. And so when we have a cloud with this type of condition, that's a sign that it's not as efficiently producing ice naturally, and it is a candidate for cloud seeding. So the second step then is to release the silver iodide particles. Typically this is done by an aircraft or by a ground-based generator. The benefit of the aircraft is that you can release the particles directly in the cloud or just above the cloud. The ground-based generator, depending on its placement and what the airflow is between it and the cloud, will vary in how well those particles can reach the cloud, which is why that third step, the dispersion step of the silver iodide, is an important one to pay attention to, is that in order for the cloud seeding to work effectively, we need to get those particles that are being released into the cloud in question. Once we get those particles into the cloud at the right temperatures that they will nucleate at, they will form ice. And as Jeff's recent animation showed, once you get ice forming in the cloud, the ice will rapidly grow larger into snowfall-sized crystals at the expense of that supercooled liquid in the cloud. And so that completes this entire process of going from the initial cloud that has some extra liquid in it to extra snow on the ground. We're basically converting that extra liquid cloud water into additional snow. Also, as Sean alluded to, you might hear about this a few times. This is just a brief step back in time to the origins of cloud seeding. This proof of concept actually came about in the 1940s. So this idea has been around for many decades. The photograph shown here on this slide from Life magazine is one of those early successes in showing this proof of concept that this liquid stratocumulus cloud could be converted to ice when it was seeded with dry ice in this racetrack pattern, which is not a very natural, pattern. So it was very clear evidence at the time that we could alter the cloud microphysics. But the real question then is, does that change in the cloud translate to a change in precipitation on the ground? All of those subsequent steps in the conceptual models proved to be very challenging to gain conclusive evidence on. Some of this is because of the fact that clouds are naturally variable. And so with large natural variability in clouds, it was hard to isolate what the effect of cloud seeding was versus what might have been something that naturally was going to occur. And over these years too, especially in the early years, there were much more limited observations and very limited computer modeling capabilities. And so that also limited some of the advances that could be made in these earlier decades. But if we fast forward to present time, first of all, we were in the field in 2017 in Idaho. We were based right there out of Boise, where you're all at now. And this project was called SNOWY, the Seeded and Natural Orographic Wintertime Clouds, the Idaho Experiment. We were able to collect, with modern day instrumentation, unambiguous signatures from cloud seeding. And in this case, we were focused on aircraft seeding. Some of the evidence that we collected here is shown in the Doppler on Wheels radar data that's animating in the center of the screen. In this particular event, the radar screen did not show much radar reflectivity because this supercooled cloud was not naturally producing much, if any, ice. So when we seeded along this aircraft track, that's the yellow line, the winds were blowing out of the southwest, so our aircraft track was perpendicular to the winds. So as it's seeding back and forth along this line, the seeding material, the silver iodide, is being dispersed downwind in a zigzag-like pattern. And Mother Nature does not produce zigzag patterns. And so this was very clear, unambiguous signature from the airborne seeding that you can see here on the screen now, that zigzag. This was This was a tremendous success and breakthrough for us to be able to collect these clear evidences of seeding, not only in the cloud, because we were flying the Wyoming King Air in the clouds to detect the ice formation and detect it with the onboard airborne radar, but we also got this information from this ground-based radar and from precipitation gauges on the ground. So we were able to really confirm that entire conceptual model from the initial ice formation all the way through to measuring and estimating snowfall reaching the ground. So this was one major success that took place in the last decade. Because of that, I feel confident saying that we've proven that conceptual model for winter orographic cloud seeding with silver iodide. However, there's still more research, of course, because as I alluded to in my key messages slide, cloud seeding does not work effectively in every cloud equally. And so a key question that we still need to better understand is where and when does cloud seeding with silver iodide work most effectively? And we also have questions forming about how effective is seeding with liquid propane? How do we confidently quantify those impacts of cloud seeding? Because not every case we're going to be able to readily see this zigzag pattern. Doesn't mean that there's not been a seeding effect. It just means that the cloud might be producing some ice in the background, and that makes it harder to detect that seeding effect with observations alone. Other questions are important as well, such as how does the cloud seeding impact stream flow? A lot of cloud seeding, especially in the western US, the ski resorts that Tom mentioned might be interested in the snowpack, but a lot of the water resource managers are interested in stream flow. And how cost effective is cloud seeding to augment these water resources? I will say there is some good news here as well, because our modeling and observational capabilities have also advanced in the last decade or so. And so we're working to address these questions and others with these new advances in computer modeling. So one of these initial breakthroughs in the computer modeling was demonstrated just over 10 years ago by Roy Rasmussen and his group when they were running these high-resolution multi-year simulations over the Colorado headwaters region. So in this map here in the center, focused on Colorado, you can see the mountainous region outlined in the red box. That's the Colorado River headwaters. They were running over that domain these high-resolution simulations down to as fine of resolution as 2-kilometer grid spacing, and comparing that with observations from SNOTELs, or snow precipitation gauges in the mountains, shown here on the right. So this is all on the same color scale. And if you look at this first panel where the grid spacing is 36 kilometers, which some of our forecast models and our climate models rarely even can get to this scale too. This is that core scale that we were limited to before supercomputers versus a 2-kilometer. You can see a very different picture in what the annual precipitation accumulation looks like over this mountainous region. On the left, in the northern Colorado region, we're getting maybe 300 to 350 millimeters of precipitation, and it's a very blocky pattern. In the center, we actually have a pattern that looks kind of like a topographical map, because the topography itself, that's the driving force for these clouds to form. So it makes sense that the clouds and precipitation would fall in a way that looks like the topography itself. And if we're looking in that north central Colorado region here, we have points in excess of 1,000 millimeters, which does line up with some of the point measurements that we have from the snow gauges. So this was really a major breakthrough, showing that we can now realistically simulate this precipitation in the mountains. And because supercomputing continues to increase at a rapid pace, we've gone from this just over 10 years ago to now running over the entire continental US for 40 years at 4-kilometer grid spacing. So this is providing us a lot of new insights into clouds, precipitation, and a whole bunch of other atmospheric features. And I know there'll be more presentations talking about this CONUS 404 type work later. But this was an initial breakthrough. From there, we then decided if we can simulate these clouds and precipitation over the mountains well enough at high resolution, maybe we can start to actually simulate seeding as well. So we built the WRF WeatherMod model at NCAR, where we now have a capability to simulate the physics of silver iodide seeding. So in this animation, it's showing 2 mountain ranges, with the white being those orographic clouds with supercooled liquid water forming over the mountains. And then the animation in the cyan color shows the silver iodide particles that are being simulated in the model. Here they're being released at an altitude where an aircraft might fly. they disperse into the cloudy region and form ice, which is yellow in this animation. You'll see it here in a minute. It's coming through, it's embedded within the cyan right now, so it's forming a lot of ice, and then it's producing snow as well. You'll see the snow, which is the green color, show up around other parts of this animation also, because this model, the Weather Research and Forecasting, or WRF model, was developed to simulate and forecast natural weather phenomenon. But what we can do with it now that we've got this seeding component in the model is we can run a simulation like this with seeding, and we can run the exact same simulation without the seeding, and we can look at the differences. We can map out spatially the amount and the locations of where the different precipitation is falling so that we can try to better quantify what the impacts of seeding on precipitation are, and do it in a controlled experiment. The other thing that's been happening besides the development and the realization we can simulate precipitation in complex terrain, and we developed WRF WeatherMod, in parallel to all of this, NCAR scientists were developing a hydrological model that was able to be driven by WRF forecast model output 2. We call this WRF Hydro. And this model simulates the spatially distributed runoff and stream flow from the WRF output. And so what we've been doing with all of these things combined is building capabilities to simulate cloud seeding impacts, not just on the precipitation that would be the output of WRF WeatherMod, but then we're using that to try to drive WRF Hydro and simulate the impacts on stream flow, because that was another key question for many stakeholders interested in cloud seeding. So this is kind of the state of the science. This is where we are today. These are some of the new capabilities that we're building, testing, and improving upon to be able to quantify the impacts of cloud seeding. So I'm going to take a moment and switch gears to summertime storm cloud seeding, since we're trying to be comprehensive here in this workshop. And I'm going to take a first step and just say there are also two modes for seeding summer storms in general. And the first is going to sound like I'm a broken record, because it's to insert ice nucleating particles, and silver iodide is common. This is the same thing that I just mentioned for winter storms. This is also a method that is utilized for seeding summertime storms as well. The other method for seeding summer storms is to insert hygroscopic particles at the cloud base. And these are typically calcium chloride or salt powders, and I will talk a little bit more about this in a moment. But first, I want to walk through this idea of why can we target a summer storm the same way that with the same materials that we might target a winter storm, using silver iodide to insert these ice nucleating particles. And it goes back to this fact that summertime storms are generally convective, which means they build deep and upward. And they do have regions in them, once they get to high enough and deep enough clouds, high enough altitudes, that are sub-freezing temperatures. And so they still also have the likelihood for supercooled liquid water in the cloud. So the basic concept here is very similar to that basic concept of winter storms in this idea that we're trying to convert more of that liquid water into ice to enhance the ice-based precipitation process. Unfortunately, I will say that this conceptual model for enhancing precipitation in summertime convective storms is not well proven, and I will walk you through some of the challenges for why that is in a few slides. The other mode, which we refer to as hygroscopic seeding, has to do with some of the principles that Jeff was presenting on before me about, in order for the warm rain formation process or the collision and coalescence process to be efficient, we really need to have a variety of cloud drop sizes, including some large cloud drops that can fall fast and collect a lot of smaller drops on the way. On this left photo or diagram here, when we have drops that are similar in size, they all fall at the same speed and they don't really collide and collect with each other very efficiently. So the concept with hygroscopic seeding then is that if we're in a situation where we have less efficient processes like this middle diagram, we can then insert these hygroscopic particles at cloud base, and they go into the cloud, through the cloud base, through an updraft. And these particles then would help form larger droplets. So we're basically trying to add larger droplets that will help initiate coalescence processes and improve the efficiency of the warm rain formation. Now, this type of seeding can be done in clouds that do get deep and have colder sub-freezing portions to them, because there still is a part of the cloud that's warmer than freezing. But this could also be done in any cloud that doesn't have that sub-freezing portion as well. But those clouds are pretty hard to come by. Most summertime convective storms, in especially the mid-latitudes here in the US, will have a sub-freezing portion. But this could still be a method for targeting those. So the science on hygroscopic seeding also is not well proven, but I will say that we have some evidence that that initial step in the conceptual model has some support, meaning that in some cases we've been able to detect an increase in the drop size. We've been able to show that there are larger drops being produced in the seeded clouds initially due to seeding with the hygroscopic particles versus those that were not seeded. But this effect really depends on what that background state of the cloud drops was before seeding. So on the left, these were clouds that had more of a maritime aerosol background particle type. So they were already producing larger drops. They were generally cleaner. They had some sea salts in them perhaps, so that we don't really detect that effect in those clouds. But the clouds that had more pollution, more continental type influences on their aerosol, had a little bit narrower drop size distribution, so they did not have those large drops. And then in the seeded cases for those, we were able to show a statistical impact in the larger drops as shown here. But that's that first step. What happens then to get the precipitation to the ground? The impact on precipitation in these cases is still pretty unclear. There were some randomized statistical studies done on this in various countries around the world that were starting to indicate that perhaps the seeded clouds were living longer and over that longer lifetime producing more rain. But there's been some recent studies in the last few years showing that the way that those clouds and storms were being detected and studied was using radar, and that the way that the radar was being used to identify those storms was potentially introducing an artifact into those studies. And so there's still some discussion and debate on the validity of those. The other challenge is that we were struggling to come up with a physical understanding and hypothesis for why this longer lifetime effect was actually happening. And so this new study showing that there might have been a flaw in the radar analysis methodology kind of helps us understand that perhaps it was an artifact and not really a finding. So this all leads me to summarize a few of the challenges why we're struggling to have the advances in the science for summertime cloud seeding that we've had in wintertime. And one of the reasons is that summertime convective storms are much more short-lived. They can be on the order of 30 to 60 minutes sometimes, generally around an hour is the average lifetime. And they have very vigorous updrafts compared to our winter storms that occur over the mountains. 1 to 2 meter per second strongest updrafts in the mountain or in wintertime storms versus 30 to maybe even 40 meter per second in really vigorous summertime convective storms. So very, very different storms. And so that leads to challenges in timing seeding appropriately if we have a very short window to target. Challenges in detecting the impacts are even greater because those really vigorous updrafts make things happen fast and make things happen in a quite variable way. And so that large natural variability in how that convective storm evolves really muddies the waters in our ability to detect an impact that was directly due to seeding and not something that was happening otherwise. Another challenge that we have is that our model simulations, which have come a long way, we've shown them to be able to reproduce the precipitation over the mountains fairly well. They do still struggle with convection, the size of it, the strength of it, and the exact location of it, because it's usually much smaller in scale to these orographically driven storms. So we still have room for improvement in our modeling of convective storms as well. And then, especially with regard to hygroscopic seeding, we have a pretty limited understanding of what the background aerosol conditions are. This is also a challenge in our winter cloud seeding too, because there is an impact on our seedability of clouds and how the microphysics in the clouds behaves based on the aerosol background in winter. But this is especially important for that hygroscopic seeding hypothesis, that as I showed, if you already have larger drops, are you really making much of an impact on the collision coalescence process? So these are areas that we really need to continue improving our research in order to continue improving our models and our understanding of these types of storms in order to see the same science advances in this area that we've been able to see in the winter clouds. All right, so before I wrap up, I have a few more points I want to make, and one of those is about cloud seeding feasibility. So, as Jeff presented and I've mentioned, we know that clouds can contain supercooled liquid water, and clouds with supercooled liquid water are generally candidates for cloud seeding in order to enhance that ice formation efficiency of snow, especially in the winter storms, as I focused on in the beginning of my talk. But we also know that these opportunities to seed how much supercooled liquid water might be in clouds and whatnot, that will vary from place to place. Some locations or even some mountain ranges are going to be more amenable to cloud seeding than others. And so it's really important that we study the climatology of weather and aerosol conditions, if the data is available, to determine when, where, and how to seed before embarking on a cloud seeding program. And not every storm is the same either. So even if you have a program, you're not going to necessarily be able to seed every storm. And so, for example, even how you might seed a given storm in one day versus the other day might change. In winter storms, for example, some might be better targeted by ground seeding and some might be better by airborne. So these are all reasons to really focus on looking at a feasibility study before doing a cloud seeding program. One other thing I was asked to speak about too, it's a very common question that we get that is based upon a physics principle of conservation of mass, is what are the extra area effects of cloud seeding? So if we seed in one area and there's extra precipitation that falls out, what's going to happen elsewhere? And conceptually, we generally rely on this conceptual diagram shown on the right that concludes that the effect outside of the target area is estimated to be very small. Furthermore, one of the reasons that the effect outside the target area is likely to be quite small is because over all these decades, it's already been challenging enough to detect the effect in the targeted area. And so with that effect in the intended area being relatively small, that extra area effect is even going to be more diffuse and dilute and harder to detect. So this conceptual model shown on the right is just a pie chart showing us the total water vapor that would be over a given region at any point in time. And not all of it is consumed to create clouds and precipitation. So if you have this whole pie chart being all of the water vapor at any point in time, and say half of it is used to create a cloud, we know that not all of the cloud is consumed to form precipitation, so we have a portion of the cloud that's then forming precipitation. And then if we're enhancing precipitation by a certain percentage, you can see that the slice of this overall pie that is being removed, the extra precipitation is removing from the total water vapor, is quite small. But I will say that now that we have some of these new capabilities, especially with the computer modeling, it does present us with some new opportunities to better address this question because it is such a common concern. And on that note, I want to make another point here that I think coordinated and collaborative science is really needed to do this. A lot of our weather modification research over the past decade has focused on local and state level programs. This has been very successful. It's been a great example of how research is being co-produced by the researchers and stakeholders alike. That means that the engagement of local stakeholders helps us address questions that are unique to those local and state regions, and it ensures that the outcomes of the research are very usable and useful. So this has been a very successful approach in many of the states that we've been doing this research on. At the same time, there is also a need now for some coordinated research at larger, broader levels across regions and larger scale to address some of these larger scale and or regional questions like extra area effects. And so in the early years, there was more federal agency support for cloud seeding research, and I think we're at a point now that we could also use more of that type of support so that we can address some of these broader questions as well as continue to address these local and state level questions. So I want to just summarize that we've made some significant advances in the science. The SNOWY data proved the conceptual model that cloud seeding can enhance precipitation in the winter orographic clouds. And we've had some modeling capability advancements, including the fact that we've shown we can realistically represent precipitation and atmospheric conditions in the mountains now. WRF WeatherMod was developed to simulate the impacts of cloud seeding on precipitation, and we're using WRF Hydro in a way coupled with WRF WeatherMod to simulate spatially distributed impacts of the precipitation on stream flow. So circling back to my key messages, the first two I just reiterated on that last slide, but I also want to remind you that more research is needed to advance our understanding of cloud seeding in summer clouds, and that cloud seeding effectiveness will vary by storm and location, so feasibility studies are needed, and we will be talking more about the feasibility studies later on. And then my last slide I want to put up is that we have developed a training module, so if you don't get your fill today and you want to take your own at your own pace, a 45-minute online training module, our COMET training program at UCAR hosts this wonderful catalog of training modules, and we've developed one on how cloud seeding works. The focus is on winter orographic cloud seeding. This QR code should take you to the website. The website's also shown on the slide, but it's a bit of a lengthy one. You will be asked to create an account, but it is free, and you'll have access to all of the training modules that are there as well.
First, I need to congratulate all of our initial speakers for their limited use of acronyms. This is a business that is pervasive in acronyms, and there have been very, very few used so far, so I will struggle to maintain that. As the indicator there shows with my email address, that's how you can reach me. When we talk about warm seeding, we typically mean clouds that develop in the summertime season, the spring or summer, convective clouds, clouds that occur when the atmosphere is unstable. The purposes are generally, as it has been indicated, increasing the precipitation, but though there's some hail damage mitigation programs here and there, I'm going to stick with the precipitation enhancement aspect of this. I want to start with our premise. And our premise is that nature is not always efficient in converting that cloud condensate that Sarah showed in that pie chart to precipitation. The efficiency of a cloud can be summarized by saying it's the precipitation divided by the total cloud condensate. So in that pie chart that Sarah showed with the cloud condensing half the water vapor, and then 2/3 of that, excuse me, being left behind as residual cloud, that would make the cloud about 1/3 efficient. When we observe rain showers and storms, the cloud never ends up on the ground. This little picture here I showed you shows an orphan anvil of a failed turret there. Yeah, then the upper part is the upper anvil for a successful thunderstorm. But this is cloud particles that will never reach the ground. Eventually they will sublimate or evaporate and return to the water vapor supply in the atmosphere. We have to be able to identify the inefficient clouds, the ones that have potential for seeding, and we also have to target them effectively and appropriately. So I'm going to talk a little bit about that. First of all, modifiable clouds, those that can be successfully altered in their microphysics so that they produce more rain, are characterized by certain things. One is they have to be cold. Dr. Tessendorf mentioned that below freezing is necessary. Most of the programs that use ice-forming particles, glaciogenic seeding, go with -5 Celsius or +23 Fahrenheit for that kind of a threshold. And these clouds are warm clouds, let me start again. The warm clouds that we can target are comprised of cloud droplets that are too small to form raindrops. And that's already been discussed very capably by Dr. Tessendorf and Dr. French. But I'm going to spend just a moment on them here. We've already heard about ice nucleating particles, so we know what those are now. And the thresholds conveniently that I mentioned here are those mentioned by others. They vary a little bit within the scientific discussions you see, but these are numbers that are right in line with that. So just direct your attention here to the diagram. The updraft is on the left-hand side of this hypothetical cold cloud where condensation is occurring and we're getting cloud droplets in that kind of blue zone. We get colder than 0 Celsius or 32 Fahrenheit. We get supercooling, but no ice. We get up to, well, here it has 0 Fahrenheit or minus 18 C, but we start to get ice above that. Minus 18, minus 15, varies from case to case. It could be even colder. In the upper part of the cloud, the ice then forms. It's got the advantage, the drop, as you would say, on the droplets get converted to ice. The particles grow through several different ice phase or mixed phase processes, get large enough, fall through the cloud. If it's warm in the subcloud region, we got rain. If it isn't, we have snow or ice particles reaching the ground. We've already talked about the collision coalescence process. This shows the larger droplet has the greater fall velocity. It catches up to the smaller droplet, captures it, and becomes a larger drop. We'll talk a little bit more about that later. For cold clouds, though, what we need to do is identify what the viable candidate is. This is for ice-forming treatment, that is glaciogenic seeding. We want an updraft because the updraft is producing condensate, which condensate means more droplets, and the droplets are what provide for the growth of the ice hydrometeors. We want a lack of natural cloud ice. Dr. French noted that when you get cloud gets cold and it gets a lot of ice in it, then the nature takes over and it does the precipitation on its own, and you need supercooled liquid water within the cloud. There are other ancillary considerations, but I'm going to not go into the weeds on those today. This is a little graphic that shows about supercooling. In the lower left-hand side, you see a cumulus cloud there with a nice flat cloud base. You see some isotherms sketched out on the side. The temperature isn't the same at all the levels through the atmosphere because there's latent heat released by the condensation in the cloud, and so it's actually warmer in the cloud at the same altitude than it is outside. That's why you have the updraft, because there's buoyancy there from the latent heat release. And so right here for glaciogenic seeding, and we're talking here now, there's the fine print here says with ice crystal engineering pyrotechnics. The threshold for nucleation is shown in the chart above the cumulus cloud there. It's from tests done by Paul DeMott at CSU some years ago. The 4 degrees of supercooling is equal to -4 Celsius temperature-wise. You see a little bit of ice, 10 to the 11th ice particles per gram of seeding agent being produced at -4, but it jumps almost 2 orders of magnitude to -6. So on the cumulus cloud there, you'll see the -6 isotherm in green. What we tell our pilots when they're going to be top seeding is to fly so that you're seeding at above -6. The ejectable flare that you would release at cloud top will fly into the cloud and descend. And so initially, it's going to actually be releasing nuclei at warmer temperatures, but because it's in the updraft, it'll be carried aloft and cool anyway. So that in a nutshell is kind of the importance of supercooling. Without it, we can't create ice, and with it, well, I'll just go to the next slide here. Easier explanation here, I guess. For cloud top seeding, the second thing we look for besides an updraft is the existence of the supercooled liquid water. The picture on the right shows what your windscreen would look like on your airplane after you fly through a cloud turret with supercooled liquid water. That water glaciates, freezes on impact at temperatures that we would see that, and so we get this accumulation of ice on the windscreen. The pictures above the cloud turret show examples of what would be considered a turret that's, well, it's visually clues that a turret still has an updraft and it's developing on the left with the green yes, and on the right, the updraft has weakened, the cloud development has stalled, there's mixing around the perimeter of the cloud, and that cloud is no longer growing, so you wouldn't want to seed that. So that's the second criteria. The third is the updraft itself. You want the updraft because it's an indication of buoyancy. As I said earlier, it's creating additional condensate that's building the cloud, and it's indicative of the cloud is still in the developing stage. You see in this diagram, the red arrows indicate the most likely indication or presence of the updraft. There will be different bubbles coming up in the cloud very often. In the early days of conceptualizing this back in the 1970s, I was thinking that, there'd be a nice uniform updraft through the cloud, and we tried some field measurements with tracers that showed that it's not a single uniform updraft through the cloud. It's variable from place to place as different bubbles come up. So if you have, again, the supercooled liquid water, the updraft, and the lack of natural ice, then you've got a cloud that potentially can be seeded. We've already seen some really nice indications of the importance of the convective life cycle in this. All of the indications that have shown show the, that's interesting. Those characters didn't turn out quite the same. Anyway, the small cloud, the developing cloud, is the one you want to target. A, it has no ice. B, it's all updraft. And C, it's super cool. And so we see the minus, the 0 degrees Celsius line shown on there. Once the cloud is matured and made ice of its own, the process is already underway. There's no need to try and duplicate what nature's already done and waste your time with that. So focus on the middle-sized cloud, as was shown early on. This is an idea, a concept of a multi-cell warm season cloud. Instead of having the individual clouds as shown here in the left panel, if you stack a bunch of those at various phases of their development, various stages of their development next to each other, you'll get something that looks like this. The updrafts get stronger as you go from the small clouds on the left toward the right. The strongest updraft can support the largest hydrometeors and therefore has the greatest potential of producing hail. We don't want anything to do with that if you're flying an airplane to see the cloud. But what we see here in the pink is where the cloud temperature is colder than -15 and ice is likely to develop naturally. So that's places where nature's going to do the job and we don't need to go there. This is a similar diagram from a different source. The white area is what we would see, or the pilots that were seeding the cloud would see with their eyes. The shaded regions, the gray and the green and the yellow, are what a weather radar, a typical weather radar might see. And what we see here is the oldest cell is on the right at time 0 in the top panel, cell number 1. And in this particular snapshot, there's no updraft left, it's raining out. So that's a dissipating mature cell. Cell number 2 is mature also, and in the dissipating stages, but we see the core precipitation echo, the yellow, is still aloft. Cell number 3 is developing, but it has precipitation. If it has precipitation and it's a cold cloud in this part of the world, that means it has ice. And so nature has already created the ice in it. And then cell 4 is the cloud that is yet developing. It has only an updraft and no radar echo. And guess what? That's the one we want to go after. 10 minutes later, the picture changes a little bit. We go to the middle cloud. Cell 1 is now basically gone. There's a little bit of rain remaining to fall out. Cell 2 has the precipitation cores on the ground. Cell 3 is still aloft. Cell 4 now has a radar echo. And cell 5 is coming along. And then the same process again another 10 minutes later. So when you combine all those, you get a multi-cell thunderstorm that looks something like this on radar. This is I've discovered that when you look for this kind of a pattern with a vertical cross-section through a warm season storm, you can find it almost all the time. Because it's so common, it reflects so accurately what exactly is happening in the cloud. And so if we were to go further to the left on this, we would have clouds out there that would not have any radar echo yet, that would potentially be seedable. In this picture, I've highlighted in yellow the supercooled area that would be amenable to glaciogenic seeding, that is seeding with silver iodide and other similar compounds. I noticed I put a couple of airplanes in there. They are focused in these small clouds, not in the taller clouds. If they're going to go far to the right in that yellow area, they would be focusing on that smaller cloud turret in the foreground, not on the area in the pink in the background. And that's how you would target these clouds. You have to be very careful not to go, well, you don't want to go where ice is because you're wasting seeding agent, but if you go where ice is, you're also going into a part of the storm that's potentially electrified. And that produces, can produce lightning. And lightning isn't likely to down the aircraft, but it can cause damage. And the main concern is engine damage that would require an expensive inspection. So this is a view from above of a similar type storm. There are two areas that I want to draw your attention to. The yellow area that you see, the oval at the bottom of the storm, is the area where we would most likely be looking for supercooled clouds to see the cloud top. The green area is where we would see that cloud base. I'm going to go back one here because we see an airplane out there flying at cloud base also. There are updrafts there. You can release silver iodide or other glaciogenic agent at that location, and the updraft will carry it into cloud and transport it in the loft until it becomes supercooled and forms ice. So that's a very good way to seed as well. The cloud-based seeding, the aircraft that do that have to take care not to go into strong updrafts. If they do that, not only are they getting into clouds that probably already have ice above the high of the cloud, but they're also in an area where hydrometeors from above could fall on the airplane without warning. So we don't want to go over there. So yes, we have more. Hygroscopic seeding. I haven't talked much about this. It's possible in this part of the world. The big criterion here is we don't worry about cloud top temperature much at all, but cloud-based temperature is really, really important. It's already been said that you need a wet cloud, a cloud with lots of water in it. We've kind of parameterized that for operational purposes to say plus 10 Celsius. That's 50 degrees Fahrenheit for a cloud-based temperature. And the reason we code it by temperature is because the ability of the atmosphere to have contain water vapor is directly correlated with temperature. And temperature is really easy to measure. And so if we measure temperature, we find a cloud base at plus 10, that means the saturation mixing ratio, the amount of water in the atmosphere is going to be very high. And we're likely to get a juicy cloud out of it. So if we can find that plus 10 C cloud that has the base that's nice and flat, doesn't have precipitation come out of it, and get into the updraft and seed with a hygroscopic material, a powder or a hygroscopic flare, one that might burn and produce small particles, then we can actually affect, hopefully, the cloud droplet size distribution in the cloud and create more larger drops. This isn't going to work in a situation where the cloud already has large droplets. That's been said once, I'll repeat it here. Hygroscopic seeding doesn't work every time just because you have a warm cloud base. There's a lot of situations, particularly in the maritime, near water bodies, where the cloud droplet distribution can be very large. Can have large sizes. I will share with you a current situation that our company is dealing with in the Middle East on the Arabian Peninsula. The humidity on over the Red Sea next to Saudi Arabia can be excessive, plus 30 or warmer, quite often. And with, excuse me, when those particles come ashore, those condensation nuclei come ashore and form clouds naturally, you would think that they would produce large numbers of large cloud droplets. But interacting with all that, we have the desert aerosol. And this ties back to something else that's been mentioned, is the importance of the natural aerosols, the tiny particles that are in the atmosphere all the time that really govern what the cloud droplet size distribution is. And so the question for us right now, we're trying to make, we are making research measurements with an instrumented aircraft to really assess the aerosols there and the implications of those aerosols for the potential for hygroscopic seating along the Red Sea. It may be that hygroscopic seating won't be effective there. The jury is still out, as they say. We've already seen a version of this diagram, so I can skip through it or go through fairly fast. I do want to point out a couple of things. One is the CCN, that dreaded acronym for cloud condensation nuclei, is very small here, a radius of 1 micron. A typical cloud droplet of 10 microns is the blue dot. A large cloud droplet is 5 times larger. That's the size cloud droplet we'd be striving for with hygroscopic seating. We want a bigger cloud droplet. And then we have the very bottom, just the edge of the big raindrop, the millimeter, or actually it's 2 millimeter raindrop there because I have R equals 1,000. Again, it emphasizes the importance of converting the small droplets into the large droplets. One other thing I'll point out is the difference between rain and drizzle isn't how wet you're getting, how fast, it's the size of the droplet. The drizzle drop you see in the upper left, this example is a 200 micron droplet compared to raindrop is much, much smaller. I've got very wet from drizzles before. Hygroscopic seating, the premise here, we want similar things. We want the updraft. We want to seat at cloud base because the droplets for the cloud are first forming at cloud base where that aerosol is rising into the saturated, super saturated environment at cloud base. So we want to tuck ourselves in close and circle there. And we want, again, that warm cloud-based temperature. We experimented with this a little bit on the summertime program up in Alberta several years ago and found that plus 10 cloud base was hard to get up there. So we bent our regulations and went to plus 7, and we really didn't see a lot in terms of a reaction. One of the challenges for cloud-based seating, hygroscopic seating, is when you find that updraft, sometimes they're quite localized, and it's hard to keep the aircraft turning tightly enough to stay in that updraft. Because when you're seating in cloud base, at least the way WMI does it, you're burning a hygroscopic flare, and you can't turn the flare on and off when you get out of updraft. It's going to burn whether you're in updraft or not. And so that's what we do. We'll repeat this kind of a treatment as long as the updraft persists, or until we have burned a sequence of 3 or 4 consecutive flares in the cloud. Then we'll move on to the next. So that's the gist of how we approach hygroscopic seating. And so we've kind of covered the winter or the warm season stuff, Derek, and now for real, you get to talk about the winter stuff.
All right, we'll try this again. Thanks, Bruce, and everybody that went before us. You really set the stage for what cloud seating is in the winter. Before I get going, I want to start out with an analogy of what we're trying to do here in the wintertime cloud seating. What would happen if I go out and give one of you guys a 1968 Ford Mustang halfback? What do? You go make it faster, right? So you start strapping on parts. You put on a supercharger, you change the exhaust out, and you start doing all this other stuff to make the car faster. And then what happens? You still need to tune it. So you get out there, you get a mechanic in there, and you start tuning the car to make sure everything that's on it is working well, is working to the top of its ability, and then you can go out and you can start racing that car. In a nutshell, that's kind of what we're trying to do with the storms that we're cloud seating in the wintertime. You got your storms that's coming across the mountaintops, your orographic storm, that's your car. That's your muscle car that's already there. And then what do? You start strapping on parts. So you have your aircraft receiving, you have your ground-based generators that you put up on the mountains. But that only gets you so far. Then you got to tune it. So where do you put those generators on the mountain? That's kind of starting your tuning. You put some weather equipment out there to see where the temperatures are ideal for seating, and so where you can operate the stuff to the best. And you start to try to optimize that storm to make it the most efficient that it can be, just like you do when you have a sports car that you go out there and you try to make a little bit faster. So when we get into this, let's talk a little bit about some of these seating apparatuses. So these are what we're strapping onto that car. Are they the superchargers or whatever it is? So we have aircraft and we have generators. There's different types of all of these, And these work at a little bit different temperature ranges. They'll work at a little bit different areas. So with the generators, we have three main types. I'll get into all these three later. You have silver iodide remote generators. You have liquid propane remote generators. You have manual silver iodide generators. And there can be other stuff that you can add to this, but that's kind of the nutshell of some of the generators that can be used for clouds. You also have aircraft, and they have different types of seating apparatuses that you can put on the aircraft. They can be burn-in-place flares, they can be ejectable flares, or they can be wingtip generators. Or there's different stuff that you can start strapping onto that aircraft to try to use that to try to optimize a storm. So let's look at these a little bit and then start to kind of peel back where you want to put these in a storm, or where these are the most efficient for when you're cloud seeding. Right here we have a silver iodide remote generator. So this is a generator that you can place anywhere on the mountain as long as you have permission to get there, and you need to be able to drive to it. So there's roads and stuff that you need to get to it in the summertime, but they can go pretty much anywhere as long as you have land to put them. And the ideal part about this is you can get them high. If you guys ever are up in the mountains in the wintertime, it's a cold morning, you get up and everybody's burning their wood stoves, right? And you go outside and you see that smoke that's rising, and then it hits a level and it just flatlines, it doesn't get above that. That's called an inversion. So if you could jump up above that, the smoke line, all of a sudden it'll be warmer there. Where you're at is cold, if you can get up there, it'll be a little bit warmer. And so what these remote generators do, if there's an inversion in place, you can get them up into that warmer air, and when you start releasing that silver iodide into the atmosphere, it can get above that inversion line. Remember, that smoke comes out and levels up. Your generator is below that, it would get up and get to that inversion line, and it won't do good because it's stuck there. So that's kind of the nutshell of why remote generators can be ideal. You can get them high up, you can put them on the mountaintops, you can get above that line. Dr. Tessendorf was also talking about some of the most ideal times to seed, and that's when you're -5. Bruce went into this too. When does that silver iodide really become active? You know, that's -5 degrees Celsius, or it could be colder. And by getting the generators up higher in the mountains, you typically get into that colder and colder air. And if it's a warm storm, or if the storm has the temperature range that those temperatures are better at the higher part of the mountain than the lower part of the mountain, a remote generator can get that up higher and just get that silver iodide directly into that colder part of the storm. That's good for cloud seeding. Another type of remote generators is a liquid propane generator. And these you can also place at higher elevations, but as opposed to the silver iodide that you need to get to about -5 degrees Celsius to work, in theory, and the research that's out there right now shows that these could start working at -1 degree Celsius. So if you have a warmer storm, and then what silver iodide would be effective at, you can start using the liquid propane, and this would start working and start developing those ice nuclei that go out and create the snowflakes and go downwind. So these liquid propane generators, they work at a little bit different temperature than what the AGI generators do, but that helps to just broaden the range of storms that you can see. Another type is the manual cloud seeding generators, and this usually involves drinking a lot of beer. So the first thing you got to do is, no, I'm just joking. These are some generators, and in this case, this is one that was created. They used the old beer keg as where the solution is, and they can put the solution inside there. It was a cheap way of doing it, and so it actually is a pretty smart idea. These work the same way as what the remote ground-based AGI generators do, except for it doesn't have all the technology that's on board to go there and to remotely turn them on, remotely turn them off, and to basically monitor everything there. It needs a person to do so. And so these are really high to get in the higher elevations, but you can still use them at some low elevation places where a farmer has a ranch or they have their house that they can go out and turn stuff on. And if there's no inversion around, they work great because they work the same way as what the remote generators do. It just takes a person to operate them, as opposed to a meteorologist that just jumps on their computer and turns stuff on remote. The final mechanism for getting silver iodide or getting a seeding solution into the cloud is using aircraft. And now if you think of that same temperature range that we have, that we're talking about, a -5 or colder, -15 maybe, you're really trying to target that area for seeding. If it's a warm storm, or if it's a cold storm, that's down by the ground, so your remote ground-based generators work really well. But then as it gets warmer, that layer keeps going higher and higher in the atmosphere. Maybe your remote generators can't reach that portion of the cloud. And so what do? You fly an aircraft. And you can get the same silver iodide into the cloud using the aircraft, and you can use three different mechanisms. You have your ejectable flares, which is in the middle portion of the picture. These are flares that once you light them, they fall from the aircraft, and they fall and burn up in about 200 or 2,500 feet. So you can see the block of air that's below you. You also have burn in place flares, which are like on the right picture. These are burned on the wingtips of the aircraft, and they stay with the aircraft so the aircraft flies, and it keeps continuing to release the silver iodide as it flies through. So it stays at the same elevation, but you get a continuous burn as you move through the aircraft. Another way of potentially seeding is using a solution the same as you put in the ground-based generators, but you burn it from a wingtip generator on the aircraft, like in the upper left picture. And this one has, basically you put that solution in there, it has a fire that burns in the backside of the generator, and that has, in that solution, has the silver iodide that then gets released into the atmosphere. So these are a few different mechanisms for actually seeding the clouds using an aircraft. So when you want to dive into and actually seed those clouds, or you're trying to fine tune everything, and you're trying to get to the what is the best, most ideal conditions to seed a storm. I always tell people that we're looking for three main ingredients for that. And the first one is there's liquid water available? And so that's in the clouds. Jeff did a great job, Sarah, Bruce, all talking about regions of the cloud that have liquid water. It's not ice, but it's liquid water. And then when we look at weather instruments, what can we use to try to identify those regions within the cloud that has the liquid water? The second question is, are the temperatures cold enough for ice nucleation? So with the case of silver iodide, we needed at -5 degrees or colder. Liquid propane, -1 degrees or colder. What can we use for weather instrumentations to start to answer those questions? And then finally, once you seed the cloud, where is that additional snowfall going to fall out? So what is the wind speed and direction that's going to basically take that additional precipitation and place it on the ground? So when we start to look at a lot of these, the first thing is the weather balloons. Don't look at the dude on there. We couldn't find any other pictures without me on it, so therefore I had to put one up of myself. We'll change that for our next slide. We'll get some more pictures of better looking people. But one thing that meteorologists use, and is pretty critical for operations, is they need to know what's going on throughout the atmosphere above them. And the best way to do that is to release weather balloons. And what these do is once you release them, it gives the meteorologist a nice little profile that they can look at. And remember when I was talking about an inversion, this is an inversion. As you go up that lower level, that's not good for seeding. If anything was below that, it wouldn't be a good case for cloud seeding, but anything above that, you can start to seed it. And so if that weather balloon comes back and says, hey, your remote generators are below that inversion, then you don't want to seed it. If they're above the inversion, then you can use them to seed. And so that's just a tool that a meteorologist can use. They can also look at the atmosphere and see where the temperature is. And so as you go up, it gets colder and colder. And here you want to be colder than -5. So you're up about here before you get into that -5 range. And so you're looking at, you're about 10,000 feet in elevation. So ground-based generators probably wouldn't be a good idea to see from this, in this situation, but you can get your aircraft above that and get your aircraft to that level. And so in a situation like this, we launch an aircraft, and then the aircraft can go out and see. You also can look at the other side and you have wind speed. So your balloons give you your wind speed and direction. So you can see where once you see that cloud, where's the transport going to happen and where that fallout is going to happen downwind. So you get the benefit of that. And so meteorologists use that so they can put the aircraft on the right flight track so they can see the target area downwind. Another thing that we can look at is a radiometer. So the weather balloons give you they can show you where clouds are, they can show you the dew point, they can show you temperature and wind, but they can't show you where liquid water is in the atmosphere. You can make some guesses, but you don't really know for sure. A radiometer, on the other hand, looks at the atmosphere and then it shows you, is there liquid water present above the radiometer? And if there's liquid water present, and you know that cloud is cold, it's below freezing, then you know that super cool liquid water is there, and so that will be an ideal situation for seeding. Here's just a track that we have of one of the storms from a couple days ago that came through, and you can see wherever the tracks start to jump up, that's where more liquid water is coming through within the storms, and that would be those big blocks are where you start to target for cloud seeding, and those would be a great idea or a great location for seeding to occur. Another thing that you can use is an ice rate sensor, and this is also showing you the liquid water in the atmosphere, or the supercool liquid water in the atmosphere. In this case, on the picture on the left side, there was a lot of liquid water in the atmosphere that all froze around the ice rate sensor. This is a pinpoint location, and it has basically a probe that sticks out, and as water comes by, the probe has to melt stuff off, and then it can tell by the change of how much energy it takes to keep it clean, where there's liquid water in the atmosphere, or where there's liquid water at that point. So if you're running a liquid propane generator that you need to place at the supercool liquid water, this will tell you yes or no if there's liquid water at that point. Another one is web cameras. Meteorologists love web cameras. You can go out and you can look at any place that you have one, and you get a visual look. What's going on? Is there a winter storm going on? Here it's very cloudy, they're in clouds, so there's some sort of moisture that's going on. And these always confirm what's happening, and a meteorologist definitely likes these because they can confirm with what all the other instrumentation has. And sometimes you can even put sticks up or other stuff, and you can watch supercool liquid water attached to that stick and watch ice grow on it, and you know that, hey, that cloud is super cool because there's ice growing, and you can use visual cues for those. Here are some other instruments that you want for basically determine wind speed and direction. You can place these at different elevations, so the instruments on the left are on top of the pole, that's on the right, and so these are 10-meter instruments that get you off the ground. You can look at wind speed, you can look at wind direction, you can look at surface temperature, and surface viewpoint. And this will tell your meteorologist what's going on the ground, if they should turn on certain generators, because the wind speed would be ideal for those generators to operate as you conduct operations. I think this is the final instrument that I have on here is a precipitation gauge. I have one more. But oftentimes where winter storms occur are in the mountain ranges, and we don't have radar coverage. So it's very difficult to see when a storm arrives and when there's precipitation starting to form. And the SNOTEL sites that we have, they measure to every tick mark on there is 1/10 of an inch. So you have to have a fair amount of snow. You have to have roughly an inch of snow before you get the first tick mark on a SNOTEL site. Plus they're an hour delayed, and it takes and they only report every hour. So you can be 2, 3, 4 hours late from the time a storm starts until you get the first tick mark on a SNOTEL site. And so one thing that you can do is put up high resolution precip gauges in the mountains, and these will measure to 1/100th of an inch, or sometimes even a finer scale than that. And you can have them report as often as you want. So you can report every 5 minutes, every minute, every hour, whatever you want to program into them. And so you get a faster response to when a storm starts producing precipitation in the mountains. And finally, I have on here is a radar. When you're lucky enough, this is one of the Doppler on wheels from the Snowy, and this was designed to go up and be placed in the mountains to observe weather that occurred in the mountains at that time. But if you're lucky enough to have a mountain range that has the National Weather Service radars that are around, then you can use the radar to start identifying when there's storms that could be potential for seeding, and to look closer at some of that aspects as well. One of the final things that we really like to dive into and look at is numerical modeling. Sarah started to touch on this in her presentation, but you can bring a new high-resolution numerical model into your cloud seeding project to really start to forecast out when is the most ideal time of that storm to seed clouds. And on the left-hand side here is a bunch of parameters that a meteorologist will use for case calling. And so this is using the numerical model in a forecast mode that's looking out into the future, and it's looking at different parameters. Where's there's liquid water, where the model thinks there's cool liquid water, when temperatures are correct, when there's precip, and where all those line up. The model then can start to show the best times for cloud seeding. Then a meteorologist can look at this and see what is driving that seeding situation, and then they can go back to their instruments that are on the ground and watch those to see if they react the same way that the model thinks they should. And if they line up, then it's a good time to call a case, and they can adjust their storm accordingly with those instruments that are on the ground. A couple of the final things that I want to get into is there's always questions about when you should seed and when you should. And a well-run project always has suspension criteria that are designed into the project. And this is for those extreme cases. If there's a lot of snowpack, should you seed? If there's avalanche concerns, should you seed? And so projects start to incorporate some of these criteria into their operating procedures. In the case of flooding, if there's two main reasons that cause flooding. One is that there's a rain on snow event. So this is when you have a large snowpack, and then you have it's in the spring of the year, or it could be in the fall year, and instead of a storm that's coming to produce more snow, it comes and produces rain instead. And that rain falls on the snowpack. And if your snowpack is already ripe, so it's ready to release the water from snowmelt, that rain will melt that snow very rapidly, and you can get some flash flooding because of the rain melting the snow, and you get a lot of water that enters the stream at one place. And so a lot of projects won't seed in these situations. It could be ideal situations for seeding, but you don't want to produce a little bit more rain that will fall on the snowpack. So you'd suspend operations if you wouldn't seed in this situation. We also look at the full size of the snowpack, and if that snowpack continues to grow and continues to get to a point that springtime runoff will probably start to exceed what riverbanks can hold, then you look at suspension criteria in that situation. So on the graphs on the right, this is just looking at some of the monitored basins, and if you had an average snowpack per year is the blue line on each of these graphs. The red line would be where you probably have your suspension criteria set up for, and then you can look at the operations or the actual snow when it falls throughout the year. And as that snowpack continues to build, it could hit the suspension criteria. And once you get close to it, or you pass the suspension, then more likely you seed you suspend seeding for the rest of the year. Some other suspension criteria that a lot of projects use are avalanche danger. When you get to the exceptional avalanche danger, you may not seed because you don't want to put more snowpack fall on unstable snowpack, so you probably won't seed in storms with an exceptional avalanche danger. Flooding, so when the USGS stream gauges reach a certain flood stage, more than likely anything upstream from that, you would suspend operations. You can suspend operations for search and rescue when they're going out to look for people that are lost or trapped. You'd probably suspend operations as that search is going on. And then there's severe weather stuff like lightning, localized heavy precip, stronger damaging winds, tornadoes, or even other special circumstances that pop up. A lot of times projects will suspend operations because of those situations as well.
Good morning, everybody. I'm Pat Golden with Heritage Environmental Consultants, here to talk about some environmental considerations surrounding cloud seeding. First, I just want to talk about naturally occurring silver in the environment. Silver is a rare metal present at concentrations averaging 100 to 1,000 parts per billion in the soil. And in fresh water, it's less than that, but it's 0.002 to 0.03 parts per billion. Again, naturally occurring in fresh water. Stream sediments are between 0.2 and 1.7 parts per million. And then freshwater concentrations, again, are typically between 1 part per trillion to 30 parts per trillion with concentrations of 50 ppt not being uncommon. Parts per trillion is 3 orders of magnitude, or 1,000 times less than parts per billion. I want to just stress that because it'll be important on another slide here. Silver concentrations in snow typically vary from 1 to 20 parts per trillion after a cloud seeding event. So that's when the silver iodide falls out of the sky into the snowpack. For comparison, that's 5,000 to 50,000 times more silver in soil compared to seeded snow, with about 20 parts per trillion or even less than that. Some localities exceed these concentrations that I just explained, but they tend to be a result of mining, photographic industry, urban refuse combustion, and things like that. So because these levels are so small, parts per trillion, in order to measure them, you have to do trace chemistry analysis. These analyses have shown negligible environmental impact from seeding operations, but we can find the silver in the snow. Again, they're such small concentrations when you go out and sample them. I think somebody showed a picture earlier, or maybe the one will come later, but you have to wear clean gear. You have to clean your equipment with acid because, I mean, your clothing has more silver in it than is in the snow where we're looking for it. So as part of the Wyoming pilot project that we worked on, the baseline in the snow was about 4 to 6 parts per trillion and about 36 parts per trillion in streams, which is just barely above detectable levels where seeding had not occurred. Again, it's far less than would be expected from other background sources of silver. So to just talk about silver speciation and how it relates to toxicity, we get this question a lot from the public. You know, you're spewing silver into the atmosphere. What's this doing to, you know, plants and animals and such? So silver ion is free. The free ion on its own is very toxic to aquatic fish, plankton, things like that. Silver iodide, on the other hand, is a salt. So it's Ag plus bound with iodide. It's insoluble. It does not dissociate in water. So that means it doesn't dissolve. Ag plus, so free silver is much less toxic to humans and terrestrial species, such as plants as well. The World Health Organization, EPA, and most state governments have water quality standards for silver, which is 100 parts per billion total silver. In a lab situation, which actually you can't do, but if silver iodide was allowed to sit in solution with unlimited time to react, you would get a solution of less than 1 part per billion of free silver. Again, that's, you know, 100 times less than the EPA limits. I won't go into that. That's kind of uninteresting. So silver accumulation and trace chemistry. Silver iodide primarily accumulates in soils or stream bed sediments, and it's found again at parts per trillion levels. Environmental sampling of cloud seeding operations have found no detectable increase in total silver concentrations above the background levels in soil, again, because we're looking for such a small amount. You can't even see it compared to natural baseline levels. It also, we've done some studies here in Idaho, actually, where we flew a helicopter out to the target area for Idaho Power and took snow samples to look for where the silver is actually being dispersed. And we found it, but in very small amounts over a large area. So again, it's not being concentrated, it's way spread out. And trace chemistry is required to detect it. So measured silver from seeding, again, this is just some data from the Wyoming Weather Modification Pilot Project that happened a few years back. Total silver measured in water during the seeding operations was the same order of magnitude as the baseline. So we went out and collected baseline samples of the water, soils, snowpack prior to the beginning of the project. And again, it was the same order of magnitude, so there was no change seen. And again, several orders of magnitude lower than values considered to be hazardous. So you can see in this graphic here, the silver is the bright red bar. EPA and World Health Organization guidelines are in that blue band, and samples from the weather 2005 was the baseline on the left, and then the cloud seeding started, and you can see that those levels really didn't change. They went up and down a little bit, but they stayed relatively the same. Here's a picture of collecting snow samples with clean gear. This is again here in Idaho. So after a seeding event, we try to go out and you dig a column and you push little vials in. I don't know if you can see it very well in the photograph, but you're sampling the layers of snow. On the right is the silver. So you can see the green bands. That's where we're actually finding the silver, which we can relate to, given the timing, to the cloud seeding experiment. Another thing that comes up is bioaccumulation. After you release silver for a long period of time, is it going to accumulate? Is it going to increase? Bioaccumulation is the buildup of the substance as it moves up the food chain. And again, toxicity depends on the concentration of active free silver ions in water. Again, silver iodide is insoluble. It's very stable. It does not break down into free silver ion. Soil sediments and water toxicity is very low, even given high total silver concentrations. Most of it's bound into that stable compound, and it's not available for absorption by any plants or animals. Free silver ion does accumulate in algae pretty quickly, but once it's in there, it binds to stable compounds, and again, it's kind of like a grain of sand because it's so stable. Even if a fish eats a bug that has silver in it, it's going to pass through their digestive tract back out into the environment. I think Bruce or Sarah talked about this one, so I'll skip that. That's again extra. Okay, so noise impacts. When we did the Wyoming Weather Modification Project, we actually had to go through NEPA to get permits to place the ground generators on Forest Service land. One of the comments that came out of the public scoping was noise impacts, and I think the Wildlife Agency was concerned with this too. How loud are these generators that you've seen pictures of? So for comparison, a 3/4 ton Chevy diesel idling with its radio and fans off is about 67 decibels. A remote cloud seeding generator, the average noise level is 65 decibels when you're standing right underneath the generator. If you move 25 feet out, that goes down to 60 decibels. 50 feet, you're down to 54. 100 feet, it's about 50, so it dissipates pretty rapidly with distance. And for comparison, 20 to 25 mile an hour winds produce 72 to 78 decibels. 10 to 15 mile an hour winds are 54 to 60. So it really just sounds like a forced air furnace in your home rather than a high pressure gas stove. So again, there's very few, if any, impacts to terrestrial wildlife, residences, and any of that. And again, ground generators are often quieter than the ambient noise level during their operation because it's often windy. You need the wind to kind of get the stuff up into the clouds, so it's pretty imperceptible. So I know Derek talked about this a little bit, but this is another comment that we've had a lot with the public in terms of suspension criteria. How do you minimize potential hazards like flooding or avalanches? It says most operational programs have suspension criteria. I'd probably say that they all do. A few reasons to suspend are unusually heavy snowpack in the target area that could cause extreme avalanche danger, unusually severe winter storms as forecast by the National Weather Service or project meteorologists, insufficient reservoir capacity. So if you start the season off with the reservoirs already pretty full, they're really monitoring that to make sure, you know, if those are getting close, they suspend operations so that there's no overtopping or anything like that. And then seeding can also just be suspended at any time at the direction of the water management agency, a utility, or the program sponsor. So for permitting, a lot of the higher elevation lands where we like to put the generators are on public lands, federal, usually Forest Service, BLM. And that placement of those requires permits. So you kind of have to work through the process. There's a bunch of different kinds of permits. Special use permits are what you need for to put the generators on the ground. But you can do a categorical exclusion. Sometimes you have to do an environmental assessment, and then like the highest level is an environmental impact statement. We try to avoid federal lands as much as possible and site them on public or state lands or private lands to avoid that. But sometimes you just have to consider it if you're planning a project, work that into the budget. We also deal with, that's the National Environmental Policy Act in California. They have a similar act. We have to deal with the Endangered Species Act quite often with that kind of permitting. And aerial operators must submit annual reports to NOAA to describe the number of hours that were operated, the amount of seeding agent that was used over the course of the season, and things like that. Common comments we get during NEPA from the public are potential downwind effects, effects of silver iodide on the environment, which we're talking about here, stream flow monitoring requirements, consultation for listed species and plants, tower design. You know, raptors they could build nests up there, so sometimes you can do some things to discourage that. Excuse me. Crucial wildlife winter range, flooding potential, concern for public water supply intake related to silver iodide, and seeding wildfire burn areas. That's another, I guess I wouldn't even call it a suspension criteria, but if an area is burned, oftentimes projects will just be suspended for, you know, a matter of years, just so you don't create a bunch of erosion in those areas. So I want to talk a little bit about stakeholder involvement and public involvement. For the Wyoming Weather Modification Project, we spent a lot of time and energy trying to have continuous dialogue with stakeholders. We did public hearings, special presentations. We traveled to little communities and do kind of what we're doing here and explain it to everyone. They had some basin advisory group meetings for the stakeholders in Wyoming. I think one of the most successful things with that project was we also had a technical advisory team. So this was a group of, the public was invited, but generally it was concerned agencies. So for the Wyoming project, and I think it's probably pretty similar here, we had, I think, Bruce, what did we have, like a couple meetings a year?
Yes.
And we had folks from the Bureau of Land Management, the NRCS, National Weather Service had some folks represented.
Forest Service.
Forest Service, University of Wyoming, Jeff and company were there. The Forest Service, multiple, I think we were dealing with 3 forests on that one. The USGS participated, the Wyoming Department of DEQ, DOT, you know, that DOT had concerns with winter seeding and how it might affect traffic and safety. Wyoming Game and Fish, and also the state engineer's office. So I think that was really effective just for everybody to keep learning about the science and express concerns and talk about it. So in summary, total silver concentrations from seeding are orders of magnitude lower than naturally occurring background levels of total silver. Silver iodide is a stable, insoluble molecule compound. It doesn't disassociate in water, and therefore it's not toxic. Again, the free silver, which people tend to not talk about on the internet, they just say silver is toxic. It's not created from silver iodide. It's insoluble. Environmental sampling of cloud seeding operations before and during operations have found no detectable increase in silver concentrations over background levels in seeded areas. Extra area effects. I think folks talked about this a little bit, but seeding has a very small impact on the water budget, the pie chart that you saw earlier, and downstream effects to your neighbors are negligible. And then again, suspension criteria really help minimize the potential for flooding, avalanches, and overtopping dams. These programs have meteorologists on project 24/7, so they're monitoring that stuff constantly. I've got a few references here if anybody's interested in looking it up. Some good publications on environmental impacts. You can reach out to me if you don't have time to get these, or I don't know if you're going to share the presentation, but I'd be happy to provide any other information. And that's all I had.
Well, we had our one-on-one this morning. You now have a pretty good overview of how cloud seeding occurs, how to measure it, how to conduct it, what the environmental effects are. Go into much more detail, but I think that's enough. And we're just waiting to see if we have any questions from Sir.
So has anybody ever experimented with seeding with propane from a plane, or is that just too dangerous?
Repeat the question. I could take a stab at that.
Right.
I think the problem is
Oh.
you're taking.
The question is, has anyone ever done seeding with propane from an airplane, aerial?
Yeah, I think the problem with that, and Jody Fisher's here and can speak to this as well, is taking a flammable compressed gas aboard an airplane. I'm not sure what kind of permitting would be required to do that. The general alternative is to use frozen carbon dioxide, dry ice, instead to achieve a very similar effect.
The advantage, I think, of liquid propane, right, is that you can seed at clouds at relatively warm temperatures, below 0 degrees Celsius, right? And if you're flying around in an aircraft, as long as the cloud, extends to temperatures of maybe minus 10 degrees Celsius or something like that, you would probably be just as effective with dry ice seeding, I would expect. And it operates under the same general principle. But I don't know of anyone that is doing dry ice seeding operationally anymore. Maybe there are some.
Right
Was
there.
that? Oh,
Yeah.
okay.
Yeah.
Great. I did not know that. Yep. Okay.
That was North Dakota who does that.
Yes.
Sir.
So at the Idaho Water Resource Board, we get some messages from naysayers, and I'm sure Kayla has too, that say that we're putting, cadmium, PFAS, all kinds of things in these. Do the flares have anything in them that's other than an agent to burn them and the silver iodide?
They do not. I'm not aware of anything in any of the compounds that is hazardous, or especially along those lines. It's curious to me how persons from the public would come up with those particular compounds.
Yeah. No one online. Oh, over here.
Yeah, thanks for great presentations. I wanted to follow up on the liquid propane and have you discuss the effects of climate change and warming. Are we likely to see warmer clouds? Does that go against the physics? Is it a natural outcome of warming? And if so, does that portend more liquid propane type of techniques or will silver iodide still work in a warming climate?
Has everybody heard the question? Just about the future of using liquid propane in a warming environment.
I can take a stab at that to begin with. If you look at global climate change, that's relatively slow change. You're looking at a few degrees at most over the course of decades or centuries that it comes along. When you get into the natural variation of storms that we have right now, there's a wide fluctuation of cold storms and warm storms. And so a lot of what we look at as what is the broadest range of storm that you can see, and how do you optimize your system so that you can seed as many of those storms as possible to create the best precipitation that you can, or the most additional snowfall. And so that's why we look at setting up liquid propane generators and AGI generators. That just broadens the scope. And also why we look at seeding from ground-based generators and aircraft. It broadens that range of storms that you can see. So if there is an increase in temperature over time, you would see that shift, that you could start to see more propane seeding. But that's one reason, if you optimize your system so that you have all these options available to you, you are in a set for that, I guess, in the future, whether it happens or not.
So again, for anybody, so we heard that, and we hear this a lot, that what's the downwind effect, and it appears to be pretty negligible, but in a more isolated area, say you've got the Tetons and you got Grand Targhee on this side and Jackson Hole right on the other side, do you enhance Targhee and reduce Jackson Hole a little bit on a storm coming from the west, or do you try to target storms coming from different directions to enhance them all? Or there's got to be a little bit of downwind effect right within a specific area, probably.
I think, if I may, I see Sarah's back online with us, and as part of the NCAR team evaluating the Wyoming pilot project, I think she has experience, or at least the team did, in answering that question. So perhaps that's one for her.
Thanks, Bruce. Yeah, so, and I also see there's a question in the Q&A coming online also, not just about downwind effect as a possible decrease, but another question came in about instances of an increase on the rain shadow side of a mountain range with any of these studies. And so I will say, on a storm by storm basis, the way that the storm is producing precipitation naturally, the amounts of moisture and liquid water in it, and each of those things can vary exactly how the seeding effect is being simulated in our model simulations. Let me just also make clear that the only way that we've been able to really look at this is with the model simulations so far on these localized case-by-case bases. So there is some variability storm by storm on if we see broad increases over an area, so to answer that question online, we do see sometimes even in the rain shadow downwind area of a mountain range, a broad increase. Sometimes we also see increases in subsequent mountain ranges downwind as well, because if that additional silver iodide nucleates ice and some of that silver iodide still reaches a mountain range downwind where there's conditions opportunities for seeding, that it might also nucleate more ice and enhance precipitation there. In some limited cases, we occasionally will see some positives and negatives, and that's where the science research is trying to understand what is going on with these storms, what makes those specific storms more likely to have an increase in one place at an offset for somewhere else, because those would then be cases that we would not want to seed. So this is where science is still, got work to do. Over a whole of a winter season, when we do these evaluations, we don't see any systematic decreases. We generally see broad areas of increase. But again, on a case-by-case, storm-by-storm basis, there might be some changes that we're still looking into more.
And I'll just add to that, because I think Sarah was talking mostly on the modeling side, but in the study that we did here in Boise and Fayette Basin in 2017, there was a case that comes to mind where we had direct observations of the impact of the snowfall coming out of the clouds actually downwind of the target area, and that was a case where Idaho Power may have not even chose to seed that case if it wasn't particularly for the research that we were doing. It was a very high wind case, and the time that it took for the precipitation to actually develop and fall out of the cloud was what is such that in very high wind cases it may not fall in the target region. And that's a ripe area for research, I think both for observations and for modeling, to improve targeting of systems on a case-by-case basis.
Just to clarify, Jeff, you're saying that in that particular case, the increase observed occurred downwind?
Yes,
Yeah.
okay. The increase occurred downwind of what the target region was. Because, right, it takes a certain amount of time once you introduce the material into the cloud for the ice to form, for those ice crystals to grow, and then to actually fall out. And if you have a very strong wind, they are going to fall out further downwind than they would if the wind was weak.
And with this case, it was one that we wouldn't have seeded naturally. It was the research part, so we did some additional seeding for that. But a side note to that is it also confirms some of our criteria that we have in place. And so this is just one of those cases where you have research that goes along with an operational program, and you start to fine tune the basis for your criteria that you actually operate under.
Yeah, right, and I think that justifies why having a lot of these additional measurements, if possible, or at times, are very useful to the program, right? Because then coming out of that, you can have a more robust program that is more specifically targeted for what you're looking at.
And I wanted to add something too, because I'm the layman here on this panel. I think a lot of times the public doesn't understand too that they're typically seeding storms that are inefficient, naturally inefficient. So they're trying to kickstart it to produce precipitation when nature wouldn't have. So you're assisting a storm that may not even drop snow on the upwind neighbor or the downwind neighbor, but by seeding it, you're encouraging it. And I mean, I don't know, correct me if I'm wrong, but it's just my observation.
Yeah.
Yes.
I have a question. You've talked a lot about cloud seeding for moisture here, but I've also read or heard about cloud seeding to break up hail, mainly in the Midwest. Is that going on in the Northwest? How does that work? It's another lecture.
Is North Dakota doing hail suppression seeding right now?
Yeah, they are, and Darren can come up and take the extra seat on the panel if you'd like to talk about it. But with Weather Modification International, we do conduct hail suppression operations. And it's the same cloud physics as what Professor French spoke to us about earlier. But what we do is, in a hailstorm, the hail generally results from a cloud that has produced very, very extreme amounts of supercooled liquid water. And there aren't very many ice particles. And so each ice particle can grow and get very, very large. And so the way you mitigate hail damage is you do the same thing. You introduce lots of little ice particles in it, and they compete with each other. And the end particles are much, much smaller, and many of them may even melt as they fall through the warm subcloud layer. So that's the premise on that. We have an active program. Of course, the state of North Dakota has the active program out there that's run for decades. And the program that our company does in Alberta, Canada, on behalf of the insurance industry, has now run 28 years, and is scheduled to continue this next spring.
Wait,
so,
is it fair to say that the science is not as advanced in that area? From my perspective, I would say, right, in demonstrating this, it's a really difficult thing to demonstrate, right? Because
we're gonna be late for lunch now.
It's not a criticism. It's just a fact, right? That you know, these storms are relatively rare.
Yeah,
And-
they're extremely complex.
And they're
Yeah,
very
and the
complex.
measurement techniques are limited. And I'm going to actually make us on time for lunch, Jeff, by saying, I want to talk more about this later today when we get to the design and evaluation side of it, because we talk about the complexities of warm season clouds and that. And so I'll defer that until then. But the question is fair. It is a very complex situation. And there is a publication that's going to come out in Atmospheric Research within the next few months, an evaluation of the Alberta program conducted by scientists at the Canadian Institute for Catastrophic Loss Reduction, using independently using the project data. And I'll talk more about how that worked also, not the details of the hail suppression, but how collecting good project data over a long term paid off in the ability to conduct an evaluation. So I think I should stop there, Tom.
And I think just the last part of your question, I'm not aware of any hail suppression in the Northwest or even the inner Mountain West.
There was interest in Cheyenne, Wyoming a few years ago, and that got quasi-serious for a brief period, but kind of died on the vine.
Before you jump on to the next one, just to follow up a little bit too with the research side of things, and one of the real benefits of the Snowy project that we had here was it was wintertime orographic cloud seeding, and that is not nearly as complex as the storms that occur in the summertime. And so when we get down to modeling and looking at some of the research on it, the models that we have can identify and track that with a lot better confidence than what they can do with the smaller scale little individual thunderstorm that occurs, because thunderstorm is very small. We're looking at a larger area of orographic lift that occurs, and that really helps out when it comes to modeling.
Kayla.
Yeah, one of the questions I get commonly here in the Northwest is why can't we do summer rain enhancement here in the Northwest? Or why does summer precipitation enhancement not work in the Northwest? Is that something you can speak to?
It's something I intend to speak to this afternoon, Kayla. So.
Sounds good. All right, we'll leave it for this afternoon.
Thank you for planting that seed.
Yes, absolutely.
Remind me if I don't
Okay,
get
we'll
to
leave it for the afternoon then.
Any more questions in the chat?
I do not see any more in the chat for right now, so I think you're still ahead of schedule.
Kayla, actually, that question in the chat from the Science Advanced side, I can just briefly address. The question being regarding snow, do we have a broad average of how much falls? I'll just add from the Snowy research project that has been discussed in my presentation and the other panelists mentioned. You know, we had 3 very clear cases with that zigzag pattern where we were able to estimate how much fell, and it varied between 100 and 300 acre feet per case. In those cases where precipitation was not naturally occurring. But we're still working on trying to evaluate the impacts on precipitation in the many other cases that we studied during Snowy. And so this is still a question that's being researched. And yes, it will be addressed more this afternoon under the monitoring and analysis, but definitely we are finally getting to the point where we might be able to put some absolute numbers to that. In the past, it was always being reported as a percentage, which if you've heard me speak on this topic before, I highly discourage use of percentages because you always have to pay attention to what the percentage is relative to in order to really understand what that percentage means. And sometimes our studies will give percents relative to seedable storms over entire winter. Sometimes it might be a percent relative to one storm on its own, or sometimes it might be a percent relative to all the precipitation and snowpack that builds in the winter. Those can lead to very different percentages. So I really think that we're at a great place now where we can try to estimate absolute value in terms of like acre feet of water, where we were not really able to do that with past methodologies. And yes, you'll hear more about those in the subsequent panels.
I'm just going to add to that. I'm hopeful, but I'm probably not quite as optimistic as Sarah is that we're that close to being able to do this. I think there's a lot that's unknown, and exactly right what she said. You know, in these 3 storms, we were able to put together good estimates based on our observations. of storms that otherwise were not producing any precipitation, which is great. But those are pretty rare storms that would be seeded in the wintertime. You know, the normal condition, if you will, the majority of storms are already going to be producing precipitation, and that's a much greater challenge. I think we are on a cusp of being able to make the first reasonable estimates, but we don't have a really good constraint overall on the system. I mean, this was from one project in Idaho. The conditions that we encountered were, you know, pretty much similar across all of these storms. And if you go to different parts of the country and you look at different types of storms that have different cloud droplet distributions and have different temperature distributions, the estimates may be quite different. And so, you know, being an academic, you know, we need more research on this to really understand it. But we certainly know a heck of a lot more now than we did 10 years ago. That's for sure.
But it's really cool that we're starting to get to a point where we can take a first step.
Yeah.
Is it correct? We'll find that out in 10 years, 20 years, 30, whatever it is. But it's really cool that we're at that point. I think that's.
I have a question online from Marta Nelson. Is there any insight into the suppression or reduction of dangerous liquid precipitation?
Dangerous liquid. What is that?
Is there
I
any?
would say freezing drizzle.
Oh, sure. Sure.
That's a great question. I don't know of anyone that is directly doing work on that. There have been groups, and I think there still are, that do like fog dispersal, right around, especially around airports or in transportation corridors, where they add ice nuclei to freezing fog or to fog that occurs below 0 degrees Celsius to get ice to fall out and disperse the fog. But in terms of adding ice nuclei to actual clouds that would be otherwise producing freezing drizzle, I am not aware of that. We just had a big project just a couple of years ago looking at freezing drizzle and freezing rain in the Northeast United States. And the idea of seeding to reduce freezing precipitation was not something that I ever heard brought up, but it's kind of an interesting idea.
I think part of the challenge is real often that freezing layer is kind of shallow and not very cold.
Which is why it's yeah.
Was there a question over here?
Yeah.
That's Jake.
So I have a question for each of the panelists and your own area of expertise from academics, and operations, and environmental health. What would you, if you had unlimited funds, what would your highest priority be for what you need to improve your area of expertise or to fill some particular gap of knowledge?
So the question is, it's for each of the panelists. It's if you could pick some research that you wanted to do or questions that you wanted answered, and money was no object, what would be your priority?
I'll go first. We've just recently started, well, I guess that's not true. There have been some environmental samples taken over the last, 40 or 50 years, but I think it's important, not because I think that this is an environmental impact, but to show the public that it's not, to conduct baseline sampling, understand what the baseline levels of silver are, and if you've got an operational program long-term, go back periodically, resample, and just put the numbers on paper to show that over time, this is not accumulating, nothing's being affected.
When I look at that,
question. There's a lot of different areas that you can look at that need improvement, but what area do you want to go in? I'm on the operational side, and a lot of that is to fine tune when we seed to make the best bulk, or you want to seed only on times that are the best for seeding, and limit the times that you're seeding elsewhere. And so operationally, I would always look at how can we spatially improve what data we're getting back from instruments that are out in the field. And a lot of this will have to do with even the creation of some new instrumentation that will be cheaper, and you can start to spread it across the field. So you can look at spatially distribute, supercool liquid water across the mountain ranges, and so you can really identify where the best locations for seeding are. This could be with liquid water, it could be with temperature, it could be with how that's integrated into the models that you have. So you can really track what's going on in nature with what's going on with models, so that you can really dive into where you're seeding. That basically gives you the best bang for your buck.
From a research and understanding perspective, I think improving our knowledge about how the system is constrained and how different environmental conditions impact the seedability, if you will, and the efficacy of seeding, I think is critical. And the way probably to go about doing that, if we at least start off thinking about like orographic winter clouds, is to repeat projects such as Snowy in different conditions around the Intermountain West that have different cloud conditions. The other part of that is to really understand the process level things of what are occurring. So in addition to going and doing additional field studies to sample different conditions, doing detailed controlled studies as best as possible in natural conditions, so mountaintop laboratories where you can make a ton of measurements, very detailed measurements of how a cloud and precipitation evolves in time, and doing this repeatedly with a long-term investment, right, will help get us to the point where Derek wants to get in terms of the operations, and it'll help get us to a point, I think, where Sarah wants to get in terms of improving our model simulations. And this also helps our basic understanding of natural cloud evolution and how aerosols impact that, which can feed back to, looking at climate change and all of those other aspects that are involved in precipitation.
Thank you, Jeff. My answer should, in theory, be the best because I've had the most time to think about it before I open my mouth.
There's Sarah after you.
Yeah, that's true. That's true. Sarah's
I'm not ranking.
I really like what Derek and Professor French have said. They both make so much sense. I too am from the operational world, work in wintertime and summertime environments. One of the things that excites me the very most right now is the advancements that have been made in instrumentation and the kinds of things we can measure them and how we can measure them. And that's largely been made possible by advances in computing technology. It's just an enormous difference from where we began this game decades ago. And with that potential, I think, comes a very bright light for the future of the technology in terms of recognizing when it can be effective and when it won't be. And the identification of those circumstances, Derek, as you said so eloquently, are very, very important. You can save your resources for the times when it's going to work. You can limit the impact on the environment. No Pat assures this at the present time with the current agents, it's minimal anyway. But it helps with overall perception, efficacy, and evaluation. I mean, there's so many microphysical things that are at play here. And, one of the big differences between the complexity of wintertime and the complexity of summertime clouds is wintertime's microphysically the process may be simpler, but the convective, but you also are dealing in large part with complex terrain a lot of the time, and that's not simple. Yeah, and so there are different things in play here. I'm starting to ramble, so I better stop, Tom. But everything that's been said is worthwhile, and I would, I think, be really excited about the not just the development of new instrumentation, but the use of more of it to get a better picture to fill that information gap where you just have point measurements here and there.
And then finally,
Can I add on that?
yes.
Okay, thanks. Yeah, so I will emphasize all the previous responses and point out that, as Bruce just said too, filling those gaps in our observations that Derek mentioned about higher spatial density of observations, gaps in our understanding that Jeff alluded to, and even though I've spoken a lot about models, I am an observationalist primarily, and so filling those gaps with observations is definitely something that would be great. Radars, more radars, gap filling radars, we call them in the Intermountain West, but even for summertime convective work, phased array, dual Doppler, dual polarization radars, there's a lot of advances there that will help us better resolve those quick evolving processes in summertime convective clouds. But in the Intermountain West, getting more radars out there to just observe the spatial patterns of precipitation in clouds and have a chance to try to observe more of those zigzags perhaps as well. But also, as I mentioned earlier in my presentation, our understanding of our aerosol, those background aerosol conditions are also really limiting. We did not have measurements on aerosol in Snowy, so while I agree with Jeff, I'd like to take Snowy and do it again in many places. I want to add on to Snowy to make sure that we get some really good understanding of those background aerosol. And that's also, of course, important in the summertime convective work too, that Bruce has mentioned that they are doing in some other parts of the world already. Supercooled liquid water observations, I think, is one of the ones Derek was alluding to that we really need to fill gaps on, because those, we don't have, I'm going to make this point again later, but we do not have routine measurements of those. And so getting that better resolved would be good. But I also want to point out that if we make these improvements to our overall understanding of how these clouds are behaving for the purpose of cloud seeding research, it also helps us more broadly, because if we understand these clouds better, that's an overall improvement to the field of cloud physics that we can then put that back into our forecast models and hopefully someday get better forecasts of the weather too, so everybody can stop doing that old joke about meteorologists keeping their job except they're wrong half the time, So if we can improve our models by improving that understanding with better observations and field projects, to me, that's the place we need to go. If we had unlimited resources, that would be great to do that. Time is still a limiting resource though, so I guess I'd need to use that unlimited budget to pay for a lot of folks to work with me, because that's the only limiting factor that I foresee for myself right now, is the time to do all this great work.
Thank you.
So, Tom, there is a question in the chat. Is there any difference in the physical properties of seeded snow versus snow that falls naturally, i.e. physical properties such as density, grain size, structure?
Boy, that's a good question. I don't think we have the, okay, so first off, my instinctual answer to that question is no. They're going to essentially be the same, and there's no reason why there really should be any difference, because all you've done in a seeded cloud is you've introduced an initial ice particle, and once that ice particle has been introduced or has been nucleated, it's going to grow through the same natural processes. Now, where that answer might go wrong just a little bit is that in clouds that are otherwise not producing natural snow very efficiently, the conditions may be such that you will be growing, that the natural processes that are occurring may be more, maybe one process might outcompete another process. that wouldn't necessarily be happening in natural conditions if there was more natural ice. Does it impact anything? No, it wouldn't anyways. I mean, it wouldn't matter in terms of, in terms of, you know, what that snowpack actually looks like while it's on the ground and all of that. But where it does come into play, or where it could come into play, are doing things like utilizing algorithms that we develop in natural snow conditions to estimate the amount of precip that falls utilizing a radar, for instance. Right? Those algorithms may need to be tweaked somewhat because the conditions of the snow are slightly different.
I largely agree with you, Jeff, based primarily on information Pat shared with us about the amount of seeding agent in the snow, and you know, a couple parts per trillion. That's such a small amount. When I think you get my head around how that can change the density or structure or something, I just can't see it.
That's a good point.
Can I just add on? Can I just add on to what Jeff and Bruce just said, though, too? I think as a way to explain what Jeff's suggestion, that if there were going to be any ways to detect it, or that they would be different, it might be in the numbers and or the size of ice crystals that fall in the seeded region, just because we are imparting that, you know, really high ice crystal or ice nucleating particle to ice crystal concentration above what the natural cloud was doing. And so the way that those might grow, the sizes they might grow to, the numbers that they might fall out in could, in theory, be different. I think that's what Jeff is alluding to. And that's where, when we do an estimation from radar of what that snowfall amount would be, it's very dependent on the sizes of the particles as well as the number concentration. So that's where we can't answer that for sure, but my gut instinct is just like Jeff's also, that I don't think that there would be really any readily detectable difference, but in theory, in a case where the process that those crystals form through could be different, we might see different numbers or sizes, but whether we'll be able to detect that anytime soon is unclear to me. Maybe in some lab cloud chamber studies, that could be an interesting way to look at that.
Thanks, Sarah. I think you said what I was trying to say a lot better than I did.
So we have time for maybe one more question if we move on to our next part of our program. And Frank?
Well, I'd just like to add to what this conversation was. So we've actually gone out and sat under the seeding plume multiple times and looked at the stuff that's coming out. And I think the one point that we need to talk about is the temperatures that the cloud seeding crystals are forming at. So, you know, if you're forming crystals at -6 versus -11, you're going to have needles versus plates maybe, and the efficiency of how the plates collect rime versus how the needles collect rime, and also how they grow based on vapor growth as well, is also a part of it. So you're going to see a little more maybe of the needly, rimed up needle kind of stuff, at least in the Sierra where we do our stuff. And so, as opposed to the colder stuff. And that's also important, I think, for aircraft seeding versus ground seeding. If you can get up and put the silver iodide at -11, -12, where you're going to get these nice crystals that have a good surface area that are going to really collect the rime, as opposed to needles that aren't quite as efficient at collecting, sweeping out the rime, you might have better precip enhancement based on what temperatures you put the ice nuclei at as well. So I think there is a way to look at it, but it's like everything else is super complex, and there's no easy way to do this.
Thanks, Frank. I think it's the type of stuff that us cloud physicists totally geek out on, but no one really cares about.
Come on. Final question. Anything?
I will go ahead. There's one in the chat. Or did you have one in here? Okay,
I just had a non-scientific question for Derek. So you put all these weather balloons way up high and they come down somewhere. Do you get calls from farmers in Iowa, or do you just put Chinese writing on them so they...
They burn up on reentry is what it says. No, they're disposable, so people, when they find them, they just throw away. I know the Weather Service has tracked some and they get some back, but yeah, most of them just end up in some farmer's field or whatever and they get disposed of.